the firmament. That's
Yeah.
so as we see. Okay, forgotten that bit then. um, yeah, yeah. So all the features you see on the moon could be the defects and the things that are on the inside of the firmament, and we're getting this projection that's that appears in front of us.
Okay. Have you
If that makes
have you
sense.
seen images of the moon? Like um zoomed in images of the moon. Have you seen some of those images?
Yes, I had a P900 at one point, and I took some myself.
Okay. I'm gonna share my screen. Uh, can you see that?
Yes.
Okay, awesome. So I've got an image of the moon. You can see it's zoomed in.
Mm-hmm.
Now, I personally believe that the moon is a sphere. And
Okay.
one of the reasons why is because if you look at the top here, can you see these craters?
Yes.
And if you look at the way that these craters are positioned, you can see that they are positioned based on the way this image is captured, that they are positioned on the top of something. Would you agree?
Sure.
And
It
if
looks like
you
that. It does.
and if you
The
continue,
perspective of
yeah, if you continue,
no, I'm agreeing with you. I'm agreeing with you. It's the perspective of the round craters that we know they're round because all the other craters are round. It
yeah,
looks like the craters are going around, at least a hemisphere.
yeah. So as you go down, you can see that the craters are in the same sort of angle position. You can see this crater here, it's more visible, and as you go down, you can see that sort of
Sure.
changes its angle. And if you reach the bottom, it's the same as the top, but just you know in the other direction, I guess. But
I'm
like
I'm
you can,
I'm not disagreeing with you.
okay,
I'm not disagreeing with you.
okay. So then, would you say that the moon is round
So
and sphere?
what again, I gave you the options there that at the very least it's a hemisphere. Okay.
A
That's
hemisphere.
one. Yeah. Because one of the features is that you only ever see one side of the moon. Okay. So if it's a sphere, right, there should be occasions where we would see the other parts of the moon, not even more of one of the craters that are on one side, perhaps. The reason why they say that we see only one side of the moon is because the moon is rotating precisely at the same time as it's moving around the Earth. So it's rotating exactly so that it always shows the same face. Now that's fair enough, but wait a minute, the moon is also moving away from the Earth, which means its orbit is getting larger. And unless it speeds up to compensate for the larger orbit, well, now that would throw out that exact precise balance. That means it only presents the same face. But for the whole of recorded history, we see the same face of the moon. So again, the moon's supposed to be moving away from us a certain I can't remember, it's only inches a year, but you combine that, the number of inches, number of over the millennia, okay, that orbit's getting bigger, and so the moon's slowing down, that precise balance shifts. So no, it's not the story we're given. It can't be true. The other thing is the distance away from the Earth, because we can just do a simple thought experiment by looking at the what's it called? The way the light drops off. It's in the inverse square law. Okay, so the inverse square law says that if you've got a light source that's a known distance or known sort of brightness, and you half the distance away from it, it gets 4 times as bright. If you half the distance again, it's 16 times as bright. Okay, well, you apply that to the moon, and the surface of the moon should be trillions of times as bright as the sun appears in the sky. So it can't be 238,000 miles away. And one of the other reasons it can't be is you can look at the bottom of the moon is cut off there, but there's a so right there at the bottom there's a bright crater, just up, if you move your cursor up a little bit, right there's a bright crater called Tycho. Okay, now mainstream science says that crater is 53 miles across. Okay, well, the thing about our eyes, we have an angular resolution of 0.02 of a degree. So the triangle formed by your eye, the top of an object and the bottom of the object, right? If that angle is below 0.02 of a degree, we can't see it. It's gone. Okay, so you can do the math yourself. Yeah, 238,000 miles is the bottom of that triangle. 53 miles is the right angle of that triangle, and so you can figure out from that the angle is 0.00128 or something like that, which means you shouldn't be able to see that crater, even though you can look up at a full moon and see that crater with the naked eye. So it's not 238,000 miles away, which means all the calculations of its orbit and all that are all out the window, because it can't be that far away.
Okay. But like, you agree with what I was saying earlier about how these craters and the positions on this on the moon
Sure
is different, which is an indicator that the moon is actually a sphere. Would you agree with that?
No, as I said, it's an indication of something, but we don't know that it means it's a sphere. As I said, let's imagine above us is a dome, okay, with imperfections on it, right? And light is being reflected off that dome, and acting through an atmosphere, and which is acting like a lens, and it's appearing like we're seeing the actual dome, right? But it's being projected as a light because it's coming through the atmosphere, and that's acting like a lens. Okay, so what we're seeing, what we could be seeing, this is one theory, is the dome. All right, that's why it never changes, because the dome never changes. Okay. Doesn't matter where you are on Earth.
Yeah.
All right. Yes, you'll see it from a different sort of rotational aspect.
Right.
But the thing doesn't change. And yes, because it's a dome, or a concave, craters sort of angle away.
Okay. But so you're saying that the reason why certain craters are positioned the way they are is just an optical illusion?
Well, yeah. I mean, have you seen the fisheye lens pictures?
Yes.
Of say somebody on Mount Everest, the 360-degree pictures. Yeah. So in order to get all that image in, it's warped so that, you know, everything is literally around, you know, is all in one picture. Yes. So you're, you know, if you're looking at a, you know, it's the same as putting a, you know, looking at a dome or the inside of a dome. Yeah. Everything is warped. Right? If you project the inside of a dome, everything is warped. So it looks like, you know, that picture you're showing, it looks like everything's curved and you know, curved around a ball, but it's not. We know it's not.
That's really interesting. And what's that phenomena called?
Well, it's the fisheye effect.
Oh, so because you mentioned something there, like when you look through a dome, it somehow makes the landscape appear as if it's round or something. Is that
what I'm saying is, if you imagine there's a you got like a nice round bowl, right? And you're inside that bowl looking up. Yeah. All the features that are on that bowl will be warped to you. They'll, you know, some will, the ones directly above, if they're circles, ones directly above will be perfectly circular. But if you look around the other side, you know, they'll look elliptical because they're not straight onto you. Yeah. Now imagine that the light from that dome is being sort of focused on you. So now you get the whole dome compressed into a small area where that light is being focused, right? And you get a small version of the bigger dome. So I don't know if that makes sense.
Kind of. But how does that affect work from our perspective?
How does it affect the?
Like, how does that like, if you're saying that this is just merely like a fisheye lens, how does that work from our perspective?
As I said, if you imagine you're in a dome, okay. You're under a dome, right? And between you and the actual dome is thick atmosphere.
Okay.
Now, again, I don't know. I've never been there, but this is one possible theory. So imagine light is being projected onto that dome and is being reflected back at us, okay, and through this atmosphere, which is acting like a lens. So literally, the light is an image of the entire dome being projected, being sort of compressed into a point. Right. So when you look at that point, you can see the entire dome.
Right. Okay.
So
this is a map.
It might look like a sphere, but it's an actual concave.
Okay. So
you look at the moon there, it could be, you know, you can't tell if it's actually convex or concave. It looks exactly the same either way.
Okay. So are you saying that this is a map that we're looking at?
This is an idea that I, you know, recently come into contact with the Iwar Anon video, Lost History of Flat Earth. I like that idea. I think yes, I think it's a map that's been burned onto this you know, onto the firmament or onto this object, but I think it's showing the greater Earth, and we only inhabit a small part of that Earth.
Because this here on the right hand side looks a bit like Africa and Europe, and then you've got this Asia here. Oh, sorry, North America. Is that what you're saying, or what do you see when you look at these?
Well, if again, this is an idea that has just not, you know, quite recently come about. But if you imagine a quarter of the moon's surface, and I can't tell you where exactly I'm talking about, but maybe the right hand side of the moon, there's those dark spots. That's their entire Earth. So a quarter of the moon, so it's like a smaller circle, about the quarter of the size of the moon, around that right hand side of the picture. That's our Earth.
Wow.
Not just, no, just bigger than that. So
this year,
yeah, that area, but it's about a quarter the size of the moon, and that's our Earth. And the sun and moon are circling, that on our Earth. Okay, essentially melting a puddle out of the ice, and the sun and moon are actually going around a magnetic center, which itself is moving around the greater Earth. So as that magnetic center moves, takes the sun and moon with it, and it melts out a different puddle as it goes around. So our Earth is constantly changing. There are continents going under the ice and new continents appearing out from under the ice. So yeah, it's an intriguing theory, and it's one I'm sort of subscribing to more and more.
okay. So because obviously this image has been zoomed in, and you said that the moon is a hole in the atmosphere. Is that right?
If you listen to what I actually said,
okay,
I don't know what the moon is. Right, I've just given you like a several ideas of what it could be. We know it's not a grey rock in space that's reflecting the sun, right? Because one of the things is
the problem with that is, like, if you actually looked at this image, you can clearly see that it is a spheroid. I mean, I don't believe it's a fisheye lens or a hole in the atmosphere, because if it were a fisheye,
okay, and well, here's the thing: whether you believe it or not, I mean, it's immaterial, because none of us actually know. This is not a floating rock in space, right?
so
things that don't make sense that they've told us are true.
You've ruled out the idea that this is a rock in space.
Yes, because an experiment you can go out and do tonight, if it was a full moon, you'd be able to do it, right? You can get a laser thermometer and see for yourself that the moon throws out cold light.
Okay.
Right, and you can go on YouTube and see lots of different people doing the same experiment and proving that the light coming from the moon is cold. Now, there is no model where something that's reflecting a hot light can ever produce cold light. That's impossible. Okay, so either the moon is producing its own light, or something else is going on, right? But it's certainly not reflecting the sun's light. And and again, the inverse square law, which, if they say no, the inverse square law is wrong, then that throws out lots of other things in science. Well, the inverse square law says that the moon isn't, would be much brighter. Well, hang on. The moon is much closer than we're told, because otherwise it should be brighter than the sun. And if Neil Armstrong landed on it, he would have been vaporized on contact.
Okay. I think you mentioned on a video of yours that you did an experiment to show that the moon has cold light. Is that right?
Well, you just heard me say there's lots of people doing that experiment, and you can go and do it yourself.
Have you performed the same experiment without the moonlight, but during a clear night?
Um, as you're saying, like as a control. So what you mean?
Well, I
Hello?
mean,
Oh,
you haven't done that. Well, if you actually
no.
did that, you would get the exact same results.
Well, no, you wouldn't. You know, because it's like, okay, the experiment I did was a piece of card on the floor, and another piece of card that was shielded. Okay, so what you would expect if the moon is not an issue, right? Both sides of the cards would be would have the same temperature, but it turns out the shade of the of I disappeared.
Sorry. Yep, I
So
can see.
you're not appearing on camera, are you?
No.
Okay, why's that?
Because I have like low bandwidth.
Okay,
And
well,
you're
shall I
lagging at
turn mine off as well? Because I've got low bandwidth as well.
yeah, yeah, that would be great. Because you're lagging a
Okay,
little bit there.
all right. Okay, hopefully that's better.
I think that's better, yeah. Um yeah, so what I'm saying is if you perform the exact same experiment without the moonlight, but during a clear night, you would get the exact same response because the exact same results because it's not the moonlight that's causing that effect. It's actually caused by heat radiation.
Heat radiation. Where's the heat coming from?
From the fact that the Earth, or the part of the Earth that you are residing in, has been exposed to sunlight for approximately 12 hours.
Right, good. So you would expect that the Earth would radiate heat at the same temperature, you know, as the whole Earth starts to cool down, and when the sun goes down, right? The whole Earth should sort of cool down at the same temperature, right? Yeah, no.
Not really, no. It's relative.
Okay, so so what makes it relative? Why, if I put a piece of card on the floor on a clear night, okay, what makes it so that you know, the part of the card will cool down more than the other part of the card?
Have you done that experiment?
No, but I will do because
Yeah,
I don't have to. I don't have to because I know, right? If I put a piece of card down on the ground, right, on any night without a full moon, right, or even with a full moon, if I put the card in full moonlight, right, right, it will the whole card would would read exactly the same, the whole card. Okay.
yeah.
Now, if it's a clear night, I put it down on the ground. The whole card would register the same temperature. Okay. On a clear night, on a full moon night, if I block the moonlight, right, on one half of the card, that area would be warmer than the other side.
I would disagree, but
Well, you can disagree all you like, but that you can go online and there's a guy who's got a an infrared, was it FLIR camera? Well, I can't remember how it means, but infrared camera, and you can see it. You can see it happening right in front of you. Where there's shadow, there it's warmer. Where there is no shadow, it's cold.
Okay, but you can do the exact same experiment on a clear night and get the exact same result.
No, that's the point. You wouldn't, because there's no model.
But have you tried that?
No, I haven't.
Okay.
Right, but I will. Just for you, I'll do that. But the point is, there is no model. There's no explanation for that to happen on a night without moonlight.
Please do what I am suggesting, because you will find
okay. Please explain to me. Please explain to me what would cause, right? You know, an area, a particular area, right, on a clear night, to have a differential in temperature, okay, and then on the, you know, on the next night when there's a full moon, there'll be a differential simply because there's a shadow from the moon. Please explain how that would work.
How you find different temperatures?
Okay, no, try and follow me here. Okay. On night one, where there's no moon, okay.
Right. Yep.
You put a piece of card on the floor.
Yep.
Okay. And you get, you know, how would you get, if you do on a clear night, put a piece of card on the floor, how would you get on one half of the card being, you know, a lower temperature than the other half of the card? How would you do that? And then the second night where there's a full moon, you put the and you get that. How would you do it? How would you get that?
So basically what you're doing is you're covering one part of the card, right?
Well, you're shielding one half of the card from the moonlight.
Are you shielding or are you covering?
Now you're shielding.
What does
so you cause a shadow, putting something in between the moonlight and the card.
Okay, when that thing that you put in between, is that like a tape or is it your hand? Like what exactly are you using?
It can be anything that causes a shadow, right, to fall. So it doesn't even have to be connected to the card. It can be above the card so that it's in place to stop the moonlight hitting one side of the card.
I mean, there could be a number of reasons why that is.
No, but I'm asking you, what is the model? What is the explanation? You're saying that it would happen on a clear night. So if you put a piece of card on the floor,
it's quite simple, actually. Right? It's quite simple.
Wait. Let me just finish. Right. Okay. You put a piece of card on the floor. Okay. And you could have whatever barrier still in place, you know, but there's no moon. Right. What is your explanation for half that card being colder than the other half?
Well, the part that is exposed is able
exposed to what?
I'll explain. The part that is able to the part that is exposed is
exposed to what?
Is able to radiate. So
exposed to what?
The heat is sent out in all directions, whereas the part that you are covering, it's unable to do that at the level of the one that is being currently exposed.
Exposed to what though? You're saying exposed. Exposed to what?
Exposed to the space around it.
Right. Well, I'm talking about, okay, you've got the card on the floor, right? And somewhere above the card, right, you've got another piece of card, right, that if there was a moon, it would leave a shadow on the card. But because it's a clear night and there is no moon, right, these pieces of card are not connected, right? So there's no moonlight. So right now we're just looking at the piece of card on the floor. What would cause one half of the card to be colder than the other half?
It's quite simple. The exposed material can freely
exposed to what? Exposed to what?
To its surrounding. It's to the space around it.
Right, but both halves of the card are exposed to the same thing.
No, you clearly mentioned that one of them is being shielded.
But no, in this case, it's not being shielded from anything. There's no moon.
Okay, and what I'm saying is when you do that experiment on a clear night, you will find the exact same results because all you're doing.
No, you won't, because. Oh,
but you haven't even tried it. How can
sorry.
you say that? You haven't.
No. Carry on. Sorry, I jumped in. Sorry. Explain. Explain what you're going to say.
It's really simple. The exposed material can freely radiate its heat to the space in a clear night, whereas the shadowed one is blocked.
Oh, but yeah, blocked. Okay, right now, right, we're not talking about the moon experiment. We're talking about the clear night experiment. Yeah.
Yeah, that's what I'm saying.
That's all we're talking about. That's what we're talking about. So explain to me,
right,
why half of that card will be colder than the other half.
Heat
right?
radiation. It's not the moonlight.
Why is that one different to the other? Why is one half different to the other?
Heat radiation.
Why is one half different from the other?
I just said it. Heat radiation.
But that you're just saying words. Heat radiation. What is causing one half to radiate less heat than the other?
Okay. I'll give you an example, right? If you take your hand and you turn your hand into a ball, like turn it into a fist, right? And squeeze it and let your other hand open and be exposed, let your palm and your fingers be exposed to, to the space around it. What you find is the hand that is a fist heats up, right? And the surface of your palm is hotter, right, than the other hand, and that is simply because of heat radiation. One hand is not being exposed to its space and therefore isn't able to transmit the heat to its surrounding space, and as a result,
you're talking about two different hands under two different conditions. I'm talking about one piece of card, right, on the ground, right, both halves of the card exposed to the same conditions.
Okay.
So show me how, in that case, how one half of that card is going to be a different temperature from the other half.
But that's not the experiment that you're doing, right?
It is. It is. Because you introduced the idea of the clear night. Yeah. So all I'm saying, right, you have exactly the same experiment, right? So
that's not your
somewhere.
experiment.
Wait. Let me finish this time. Yeah. Somewhere above that card on the floor, right, is another piece of card that would block the sunlight or the moonlight if the moon was there. Okay. So without the moon there, that piece of card is having no effect on the card on the floor. Right. So because all it's there to do is block the moonlight when the moon is there. Okay. When the moon's not there, it's got no effect on that piece of card. I want you to tell me, right, how half of that card, on a clear night with no moon, right, will be colder than the other half of the card.
Let me share my screen. I'll show you what I'm talking about. Because I'm not sure how familiar you are with heat radiation, but it's a simple thing to understand and grasp. Can you see my screen?
Not yet.
Okay.
Okay, so
Can you see this?
Why has the moonlight cooled? Okay, let's see.
So can you see this image on the right here?
Yeah.
So this is a reason why the moonlight is cold. Okay.
Right, but this isn't the experiment I'm talking about. This is a very contrived experiment.
No, it's not. There's no ill intent involved.
Yes.
There is no ill intent involved. Is this not your experiment? Half the
No,
card.
you're trying to say it's trying to say, right, that the whatever's blocking it is trapping the heat, right? So, and so it's not or it's radiating away in one example, and the other side it's not radiating away.
That's exactly it. It's heat radiation at the end of the day.
Right. Well, what I'm trying to say is where if the blocking material, right, is away from the thing you're measuring, okay, it's away from the thing it's measuring, so it's not affecting the thing that's being measured, okay, not directly. It's not stopping any heat radiating away from radiate. It's not stopping any heat radiation. It's effectively away. All it's doing is blocking the moonlight. Okay, that's all it's doing. It's not affecting the thing you're measuring one little bit. But this is the thing, right? We're not talking about this experiment right now. All we're talking about is the example you just gave.
Right.
The clear night. Okay. So you put a piece of card on the floor, right? You have the piece of card above it. So again, it can't affect it in any way. And it's not blocking anything because there's no moon, right? You've got to try and explain to me how one half of that card will be cold and the other half will be warm.
Which card? Because you said there are
the
two
card
cards.
On the floor.
The card on the
card
floor.
on the floor. The card above it is there to block the moonlight if there's a moon. But because there's no moon on this clear night, there is nothing to block. So that piece of card has no effect on the card on the floor.
Okay, so there's a card on the floor and there's a card above it.
Yes.
How much space is between the card that's
10 foot.
10 foot.
10 feet.
And that's experiment that you did with the moonlight.
Well, no, I did it with two pieces of card the same, so that but it doesn't matter. All it's there to do is block the light.
Okay. So if you did the exact same experiment on a clear night, you would have the exact same results. And the reason why you'd have the exact same results is because, again, I've already addressed this. I don't understand why
you haven't
to comprehend.
No, you haven't.
I have. It's a heat radiation.
Yes, but both sides of the card would radiate heat in exactly the same way. What's the difference? What's making the difference on one half of the card to the other half?
Heat radiation. I just explained it to you. So again, no, you're just saying a word, right? Which will act on both sides of the card at the same time in the same way, because there's no variable. So why does one half? Okay.
What?
I'm sorry, but that doesn't make any sense. Like,
okay, if you get that piece of card and you shine a hot lamp on that card, right? Then take the hot lamp away, right? The card would radiate heat away at the same rate on both sides of that card. Yes or no? Yes or no?
Yes.
Yes. Right. So show me an example of where you can do that, right? You can heat that card up with a lamp above it, take the lamp away, and one half of the card cools down way faster than the other.
The problem with that is, right?
There's no problem. I'm asking you a question.
No, there is a problem. The problem with that is you're assuming that the moon is somehow
No, we're not talking about the moon. We're not
Yes.
talking about the moon.
Yes, you
We're
are.
not talking about,
You
no,
talk-
we're talking about your example of
But-
a clear night without the moon. Let's
but
stick with that first.
But he
Yeah,
talked about
because you're saying, we'll stick with that one first, because your assertion is if you do it on a clear night, right, you get exactly the same results. I'm trying to get you to explain how you get a differential between one half of a piece of card to the other, right, with no other variables.
and I explained it, heat radiation, but I know
No, you haven't. You just keep saying the word heat radiation. You keep saying the word heat radiation, but you don't explain how the heat radiation will differ from one side to the other.
Okay, the problem with what you're saying.
There's no problem with what I'm saying. I'm asking a question.
No, it is, because the example that you gave, you said that there's a heat lamp involved, right?
Yeah, that was just to say, to try and get you to understand.
Right. So why did you? So you're basically inferring that the heat lamp is the moonlight.
No, I'm not. I'm not. The moon is out of the picture. We're talking about, because you keep saying about heat radiation. I said about the heat lamp to basically focus this. Yeah. So I've got a piece of card, right, on the floor. Okay. The floor underneath is, is radiating the same amount of radiation across the whole face of that card. Agree or not disagree?
I agree.
So the piece of card on the floor is radiating the same heat over the whole face of that card. Agree or disagree?
Agree.
How does one half of that card start radiating, or how is that one half of that card colder than the other half? How do you get that?
Because the card on the ground has less surface area, and as a result of that, less.
Hang on, less surface area. It's the same card. One piece of card on the floor. How does one half of the card be warmer than the other half?
One half of the card. See,
yes, it's a piece of card, right?
Piece of card. So that you're talking about two separate cards.
No, I'm talking about one piece of card, right, on the floor.
Okay. And
literally, we've both agreed that that piece of card would radiate heat equally across across its entire surface. I'm asking you, what's your model to explain how one half of that card can be colder than the other half?
Okay, I'm going to reiterate what you said, and let me know if we're on the same page. You have a card. You place the card.
Piece of card.
Let's not use piece of card. You have a card, okay? And a card has two sides, right? You place the card on the ground. Let's say grass or concrete, doesn't really matter what the surfaces.
Doesn't matter.
Place the card on the ground, okay? And you step away from it, and then you come back to measure it or something. Is that right?
Yep. So I want to know.
And you identified that the card that is facing upwards has more or less heat.
I'm saying that piece of card, I'm not talking about the underside of the card that's sitting on the grass. I'm talking about the top of the card, okay?
Okay.
I want you to explain how half of that card is warmer than the other half.
Oh, okay. So we're only talking about one side of a card. And
of course, I've not been saying about the underside.
Oh, right. Okay, I got confused there. So you're talking about one side of the card. And in your original experiment, you covered half of that one side, and you found that on one side it was colder than the other. And now you're saying, if we do the exact same experiment on a clear night, are we going to get the same results? If we cover one half of the one side of the card on a clear night, are we going to get the exact same results? Is that your question?
Yes, you're saying
And
you will, and I'm saying I can't.
my answer has always been the same. Heat radiation. Because you're covering
Please,
your
no.
mask.
Explain to me, right? In that scenario, how you get a differential on that piece of card? What is making the differential?
Heat radiation. It's one side.
Why?
Because one side is exposed to the space around it, which enables it.
Well, both sides are exposed to the space around it.
No, because
equally.
No. You said that one side is covered, right?
No, I said there is a card above the piece, a piece of card on the floor, right? Has got not connected to it, right? Has no relation to that card because there's no moon, so it can't cast a shadow. It's literally above the card, got no connection to it whatsoever. So there's no lack of exposure or anything. Okay.
And is the card on the ground has more heat or less heat than the card that's above it?
It doesn't matter about the card above it. Yeah. It's just a piece of card or anything that will be in the way of the moonlight. It could be a tree trunk, right? That's like 100 yards away. Yeah. If that tree trunk casts a shadow on half the card, yeah, even if it's 100 yards away, right? The shadow of the moonlight will be warmer than the moonlight itself. So the tree trunk is not interfering with the card, right? And we are going to agree here, and we already have agreed, that the piece of card sitting on the ground on a clear night with no moon, right, will be the same temperature across the full surface.
Yes.
Okay. Right. So that tree 100 yards away, which is now not casting a shadow on that card, right, has no effect on the card. Are we agreed?
Yes.
Right. So on the clear night, with, let's say, the tree, right, 100 yards away, how does one half of that card stay warm and the other half of the card get cold?
Because again, as I already mentioned, one part of the card, sorry, the card that is covering the other card.
No, we've moved away from that now. We've moved away from that because that seems to be a problem for you. Yeah.
Okay. Yeah.
We're talking about is a piece of card on the floor right now, and there's a tree 100 yards away. So on a clear night, the tree has got nothing to do with anything. It's 100 yards away. It's got no effect on the piece of card. The piece of card's on the floor in the middle of a field. Okay. All right. With a tree 100 yards away. So on the clear night, that card will be the same temperature across the entire surface. Am I right or am I wrong?
You're right.
Right. Okay. So please explain to me how we get from you agreeing with me that the card will be the same temperature across the entire surface to, right, that half the card will be cold and half the card will be warm. How do you get to that from on a clear night?
I don't know what else to tell you. Like the heat radiation, it's just,
yeah, no, you keep saying heat radiation, but you're not explaining how heat radiation will cause a differential on that card. Because you've agreed, we've both agreed that in those circumstances, that card would radiate equally on both sides of that card, wouldn't it? We've agreed on that, haven't we?
Yes.
So what is the variable, right, that you claim will, because you now say that if I put that card down on the ground on a clear night, somehow half the card will be cold and half the card will be warm.
Yes.
How?
Heat radiation, because one has.
Well, give me the mechanism.
One has space around it, the other doesn't. if they had the exact.
No, it's the same card. It's the same card. The same card has space either, all round
No, it
it. It's the
doesn't.
same
No,
piece of
it
card.
doesn't. No, it doesn't. If
How?
if one card has enough space exposed around it, then
No, it's the same card, not one card. We're not talking two cards here. We're not talking two cards here.
Okay.
We're not talking about two cards. We're talking about one piece of card, yeah, sitting on the grass in a field, right, on its own.
Okay.
Right. You've got that, have you? One piece of card on its own.
Yes.
Right. So we've agreed that the heat radiation will be equal on that piece of card all over the surface, yeah? In that scenario.
One side, yes. The underside.
I'm only talking about the upper side. I'm not talking about what the side that's on the ground.
Sure, yeah.
All right. So across the entire surface of the upward facing piece of that of card, right?
Yep.
It's going to be equal. But you're saying, no, it's not going to be equal. Half the card's going to be warm, half the card's going to be hot. How is that? One side of that card, the upper face, is going to be hot. One side of the card is going to be cold. How does that work?
Because you mentioned earlier that in your experiment, one part is being covered and the other isn't, right?
Okay, but we're not talking about the experiment right now. We're talking about your experiment.
That's exactly
we're talking about your experiment now.
But that's what
we're talking about. Your experiment.
I'm saying
no. Forget the moon experiment, because we're talking about a clear night now, because that's what you introduced.
I'm saying if you took the moonlight experiment and you did it on a clear night, you would get the same result as what I'm saying.
What? That's what we're talking about. We're talking about a night without any moon.
Talking about this entire time.
Let me finish. We're talking about a night without a moon, right? Is that right?
Yes.
Okay. A night without the moon. You take a piece of card, you put it on the grass.
Right.
Okay. There's a tree about 100 yards away.
Mm-hmm.
That's the only tree in the field is 100 yards away. So the tree does not affect the piece of card in any other way, right?
Right.
Okay. So what I'm trying to get to is your explanation, right? Because you're asserting that on a clear night you'll get the same results as a moonlight night, yeah? So I want your explanation for how one half, the left-hand side of the card, can be warmer than the right-hand side of the card in that field, right? 100 yards away from a tree.
Look, we can agree to disagree.
No, we're not going to agree to disagree, because you introduced this idea, right? But you can't explain it, because you just keep saying heat radiation, but you're not explaining the mechanism how heat radiation will be differentiated on two different sides of the same piece of card.
Look, I've tried my best. I really did.
No, you haven't explained it. You just said heat radiation. Explain how one half can radiate more heat than the other. Explain that.
Because one area is exposed and the other isn't.
Exposed to what?
To the space surrounding it.
Both sides of the card are exposed to the same space.
I'm talking about the moonlight experiment.
And I'm talking about your experiment. I'm talking about your experiment on a clear night. In our clear night. No, wait. On a clear night with no moon. Clear night with no moon, right? You're saying the same results would happen on a night when there is a moon, okay? So I'm saying on a clear night with no moon, tell me how one half of that card will be warmer than the other, because you say it'd be the same on a moonlit night, okay? Explain that to me. Very simple. You keep saying it's so simple and I must be stupid or something, but here, explain that to me.
I mean, all I'm saying is if you take the moonlight experiment that you've done and did it on a clear night, you'll get the same results. That's all I'm saying. We don't need to go further.
Well, you're wrong. you're wrong because
Wow.
right. I'm telling you, this is the example. Here's the example. Just let me finish. Right. We put the card on a clear night, right, in the middle of this field. Okay, a tree 100 yards away. Right. Now, on that clear night, we can take a laser thermometer, fire it on the left-hand side of the card. It would read the exact same temperature as on the right side of the card on the clear night. Yes or no?
Yes.
Right. So we come back the next night, right? The card is in exactly the same spot. Okay. But this time it's a full moon. And the moon is positioned so that the tree that's 100 yards away is casting a shadow on the left-hand side of the card. Now we measure it. And on the left-hand side of the card, it is warmer than the right-hand side of the card. So what I'm saying is no, it wouldn't be the same on same results on those 2 different days, because the variable here is the moon and its shadow. Do you get it now?
I do.
Thank you.
Interesting. But I would still suggest that you do the experiment on a clear night, and
I don't have to. It's common sense to know that if I put a card in, in the middle of a field, right? Nothing else acting on it. I can measure both anywhere on that piece of card it with the same temperature.
Sure, you can make the argument that common sense this and common sense that, but if you are someone who
if I had my laser thermometer now, I'd do it right now and say, yes, it's true.
Okay,
but I know I don't have to.
What I'm saying is, if you're someone who is truly looking for truth, you would set aside confirmation bias and actually do, even if it's common sense, supposedly common sense, you would still go through with the experiment.
Are you saying it's not common sense? It's not common sense that if you put something down in an environment where there's no other factors involved, right, that all of a sudden somehow one half of that card will be warm and the other half will be cold? You're saying that's common sense. That's what would happen.
Yes.
Or is it? Oh, is that you're saying that? Oh, good grief!
Because
unbelievable. We've agreed.
There are many things that it may appear to be common sense, but until you actually do the experiment.
But not when it's repeatable. Not when it's repeatable. Right. And again, you can go on the internet and see lots of people doing exactly the same experiment and getting the same results. It's repeatable and reliable. Okay. And something you can test yourself. But I'm not trying to force this on you. You can go out and test it yourself.
I disagree. And look,
well, yeah. I'm sorry, that's not a real argument. I disagree. You've got to have something to say. Well, I disagree because
you're not willing to test your own supposed common sense. I would highly recommend that you do the exact same experiment on a clear night, and if you find that the exact same result,
and I'm trying to say, I know, I haven't. It hadn't crossed my mind, but I challenged you to explain, right, how you could get that differential on a clear night.
I have,
and you haven't.
I have.
No, you haven't. You just keep repeating radiation, right? But you haven't explained the mechanism that causes one side to radiate more than the other.
I have, and you refuse.
No, you haven't. You haven't. You haven't. You said, well, the one side is exposed more than the other. No, look, I'm saying it's in a field. How can it be one side exposed more than the other.
Look, we can go.
And then you agreed with me.
Look, we can go back and forth, but I don't see how this conversation is progressing because look,
because you won't see sense, even though when you agreed with me,
right,
right, that there is no difference between the left and right side of the card when it's in the middle of a field, right? Then you go back on it and say, well, yes, there is, because one side's exposed to something and the other isn't. But you won't explain what it's exposed to and what the other. You're being nonsensical.
I'm not being nonsensical because look, the thing is, I have explanations and I've explained them. If you refuse,
well, you haven't explained it. A piece of card in the middle of a field. What makes one side, right? One side, just no other variables. One side somehow radiate more than the other.
and you're saying that and you're saying none of them is being covered.
Nothing's being covered. It's in the middle of a field.
Is that experiment the same as the moonlight experiment?
Oh, for crying out loud, sir. Seriously. You introduced the idea of doing it on a clear night and getting the same results. Yeah. I'm saying, and I give you a scenario where we do that, right? The only variable is that, okay, the tree 100 yards away, right, is in the same, is in both experiments. The tree is 100 yards away, but on a clear night, the tree has no effect, right? The tree is just literally a tree that's 100 yards away. The piece of card is standing alone in the middle of a field, or sort of lying on the grass in the middle of a field. On the clear night, you go to that piece of card of your laser thermometer, and you can pass that laser thermometer over the whole piece of card. The temperature would measure exactly the same over the whole surface of that card. Right or wrong? Yes or no?
I'm not sure about. I'm not familiar with the tools and equipment that you're using to measure the card.
It doesn't matter. All right, you put two thermometers on the left and right side of the card. Yeah.
Look, I really want us to come to a. Look,
well, you're not answering the question.
Look, I've tried my best to answer it, and if you refuse to
you've not answered the question,
then.
Well, I'm just asking you, yes or no? Am I right? If that piece of card's in the middle of the field,
no, you're
and
not
there's
right. You're not right. No.
Okay, so explain to me. Explain to me what the difference is between the two thermometers.
Because we're back and forth here, and I really
yeah, because
I really want to ask you some other questions as well, if you don't mind.
Well, it doesn't seem like it's worth it if you're going to say nonsensical things and not back it up with anything.
I've tried. I explained heat radiation. You refuse to accept it. And
yes, you keep saying the word. You keep saying the word, but you don't explain the mechanism by which on the same piece of card with no other variables, that one will radiate more than the other. Yeah, one side will radiate more than the other side.
With all respect, I think you're being a little dishonest here, because you know what I was talking about.
I'm not being dishonest. You're the one who's not explaining yourself.
I was talking about the moonlight experiment, and
but you introduced a second experiment, didn't you?
No. All I did was change the setting. Okay, that's all I did.
So did I.
No,
so did I.
So introduced new variables and then correlated with the original experiment. So no, that's not what you've done.
Okay, the original experiment, right, is a piece of card on the floor, a tree. In this case, we'll make it a tree because, right, just to remove some arguments you might have. A tree 100 yards away is blocking the moonlight from hitting one half of a card. Okay. Right. Now you can have two thermometers sitting on the middle of that card, right? One, right, in the shade of the moonlight is going to be warmer than the moonlight, exposed directly to the moonlight. Okay. Now, if you go on, leave that experiment as it is, right, and come back the next day when there's no moonlight, right? The tree's still 100 yards away, not affecting the card in any other way now, right? The thermometers will read exactly the same. Now, you're trying to say that somehow on that second night, when you go back to that piece of card, right, one side of that card is going to still read hotter or colder than the other side.
Right.
I want you to explain, right, on that clear night, what is causing the differential?
Heat radiation.
Okay, you're saying the word, but
Because
tell me the mechanism.
But like the mechanism is quite simple. When an area is exposed to its surrounding, to the space around it, it is able to transmit heat in all directions.
Sure, I agree.
And
but
when
why is one side of that card,
and if something is covered or barricaded,
covered from what?
not exposed,
Covered from what?
it's not going to do that.
Covered from what? The tree that would cast a shadow if there was moonlight is having no effect on that piece of card, because there is no moon now on the clear night. There is no moon there now to cast a shadow. Right, so the tree has no effect on the card on the clear night. So what is causing the differential on the clear night?
The shadow that's being cast is going.
There is no shadow.
No. I'm just getting a better understanding of the original experiment. So the shadow is hitting one part of the card and not the other. Is that correct?
One half of the card is being there's a shadow from a tree 100 yards away. Yeah, the shadow of that from that tree is hitting one half of the card, and that half of the card is warmer than the card that is not being obscured. So, right, on the next night when there is no moon, so there is no shadow, the tree is having no effect on that card. Okay. I want you to explain how one half of the card is still warm and the other half of the card is cold.
And you're saying that the surface of the card is exposed to its surrounding.
Yes, both sides of the card.
Okay. And one has moonlight hit on it, the other one.
No, we're talking about the clear night now. We're talking about clear night now. Yeah, because you said it'll be the same. Okay, clear night is still in the middle of the field, right? The tree is still 100 yards away, but there's no moonlight. Okay, no shadow on the card. So both sides of that card exposed to exactly the same elements. So why are you saying one side is going to be warm and the other side is going to be cold?
My understanding is that there was something blocking, because that's what you said originally.
That's when the moon is there. The tree 100 yards away is blocking the moonlight. But on a clear night, there is no moonlight. So the tree is doing nothing.
Right. And what's your point?
My point is that you are wrong when you say if you do the same thing on a clear night, right, you'll get the same results. You would not get the same results because both sides of that card will be exactly the same. The only variable is that there's moonlight, and one half of the moonlight is is exposing what is being exposed to the card, and the other half isn't. So there's a temperature differential in that case, meaning that the moon's light is cold and the shade of the moonlight is warm or warmer.
Well, sure. I mean, well,
that's the experiment. Thank you for agreeing with me. Now we can move on.
But that's just radiation from the moon.
That's what we're talking about, aren't we? We're talking about the radiation, the light from the moon is actually colder than the shade of the light from the moon. And this is what that experiment shows.
It doesn't show that the moon is a light source.
Well, it's showing that the light that's coming off the moon is a cold light, and there is no physics to explain a hot light.
A cold light. Oh no, it's not.
There is not physics to explain how a rock can reflect hot light and make it cold. Unless you can tell me the physics that will do that. Can you tell me the physics that will do that?
We can agree to disagree.
Well, that is the cop out of somebody who can't argue.
No, because I've tried. You just refuse.
We've agreed that the experiment shows that, and now you're backtracking again.
No. Because if you actually play this back, you'll realize that you said one thing, and then you keep changing it. How? I change it to try and make it clear to you, because you don't seem to understand. A minute ago, you thought I was talking about the underside of the card. But the new experiment that you just created right now, you haven't yourself even tested it. You haven't tested it. And so you're just making up things as you go, and that's unfair.
Well, no, we agreed. We've agreed.
And then you call.
We've agreed on it, but you've agreed on it, right? You agreed on it. I asked you for your agreement every step of the way.
No, this is just a theory. You haven't tested this. So I want you to go out there and test it. Otherwise, don't bring up theories you haven't tested, okay?
I want you to go out and test both of them.
No, that is not.
I want you to go out and test both of them.
I will. And you know what? I'll get the exact same results with the moonlight.
Please do.
And it will be the exact same thing.
Please do.
And if that were the case, would you drop this moonlight theory?
Well, no, because I've actually done the experiment. No, I haven't done. I haven't done the control.
No, you haven't.
I haven't done the control that you suggested, right? But that is the only variable in this case.
I want you to do the control and come back to me, because you will find it.
Okay, I will.
You'll get the exact same result. And if
now you're telling me what I'm going to find. You're telling me what I'm going to find. Sir, you're telling me what I'm going to find when you haven't done the experiment yourself, have you? So don't tell me what I'm going to find and complain that I'm saying things because I haven't done the experiment, because you're doing exactly the same thing, aren't you?
No, because I have.
You have done the experiment?
Yeah, I read on other people's experiments.
Oh, you've read about it. Oh, so no, you're having a go at me because I haven't done the control experiment. You haven't done either experiment, and you're telling me what results I'm going to get.
Because I trust peer-reviewed sources.
Okay, peer-reviewed sources aren't doing this experiment.
Yes, they are. And
they're not.
And they tested it, and they said that it's simple, it's heat radiation. You'll find the exact same results. But you know what?
Okay. Send me the peer-reviewed science, right? Whenever you get a chance, send me the peer-reviewed science that shows exactly how it works.
Okay, sure. I'll try to find it and send it to you. Yeah. I don't. So you are a flat earther, is that right?
Absolutely.
And if there's compelling evidence to suggest that the Earth is round, would you accept it?
I have grown up in the model of the Earth being a spinning sphere in space my entire life. Yeah, I was a student of science. I spend my time listening to science lectures, and my job was implementing scientific theory. Yeah, so yes, I know the model, and no, I would not be convinced by the model, because it is just a model.
Yeah, you're right. It is just a representation, because in one of your videos you mentioned how the images that we obtain from NASA are CGI and Photoshop. Is that right?
That's not me saying it. It's Rob Simon, the guy who actually creates these images. He said it, not me.
Okay, I can explain that if you like.
Well, you don't have to explain it. You can't explain it because Rob Simon, the actual guy who makes it, explains it on it in an interview.
But
You
like
you can't now say, well, I know better than him, because that's his job.
okay, I can explain it. So the pictures of Earth that we all grew up with are actually outdated. So they've existed for a long period of time. And during the time that these pictures were taken, um, they didn't have digital image processing technologies of today. And as a result, they needed a team of, very skilled professionals in uh, how would you put it, image formatting, to make the images that they actually captured into something that we can all interpret. Does that make sense?
Have you actually listened to the interview by Rob Simon?
Yes.
Okay, did you not hear what he said in that interview?
Just because someone says that they photoshopped the images doesn't mean that
No, he said more than that. He
okay.
said more than that. He explained exactly how he created those images. Yeah, he created the images from data, not photographs, from data.
Yeah, that's what, yeah.
Wait a minute.
Yeah, I agree.
He took ones and zeros and decided that because, let's say, the numbers representing phytoplankton, right, is high near the coast, he's going to color those blue, and the ones that are low, he's going to color them darker blue. Yeah. He said he put in the reflection of the sun on the water. He put that in. He put in a layer that simulated the atmosphere. He put that in. Okay. He took a cloud map and then made it look like the cloud map was above the surface. He did that. He said, I hit Command Z a lot. Command Z is to move up a layer in the Z direction, the Z direction. Okay.
Right.
He did that. Right. He manufactured that image from data. Right. It is not a photograph.
Okay.
And then also when you look at the photographs, right, the images, what you'll find is the clone stamp tool used to make the clouds. Clouds do not replicate themselves across the earth naturally, right? Then when you look at these clouds and you see that they've been clone stamped in various places around the image, it's Photoshop. And then when you see the word sex written into the clouds, well, there's nobody writing massive clouds with the word sex in them.
That's very explicit. Yeah.
Sorry?
That's very explicit. But I mean, I'm sure you'll find different variation. I mean, clouds, they form, things that we're familiar with all the time. Just the other day I saw a cloud form into like
I'm talking about clone stamped clouds. The exact same cloud formations, right? Placed in various places. You can actually take one cloud formation from another and then put it over the top, and it's identical. It's clone stamped. I can do the same thing with Photoshop.
Okay, but what I'm saying is, there are limitations and restrictions to the cameras and the scientific instruments that NASA uses to capture these images. And as a result of that, they make adjustments to the images so that the images appear, so the images that can be interpreted by us. Does that make sense? So NASA may collect data that are just zeros and ones, but we can take that data and convert it into something that, convert it into an image. Does that make sense?
But you're still talking about taking numbers, right? And turning those numbers into a picture.
Are you aware of
manually?
Are you aware of the Fourier transform?
Yes, I am.
Okay, Fourier transform is a series of numbers. Okay, and when people see those series of numbers, they all they see is a series of numbers. They don't see anything else.
And you're trying to say you can make a hologram from it.
You can make an image out of a
hologram
transform.
from it.
Do you agree?
Indeed. We're not, yes, but we're not talking about Fourier transforms here, are we?
Right.
Are we talking about Fourier transforms? Are you saying that these satellites that supposedly giving this data are recording that data holographically? So, and Rob Simon is actually taking that holographic data and manually converting that into an image. Is that what you're saying?
Yes.
Okay.
I know. To a layman, it appears as though, like, there's some great conspiracy. Why is NASA relying on zeros and ones to produce an image? But images, especially digital images, you can rely on other instruments to form images. You know that.
Are you a computer programmer?
Am I a computer programmer? No.
You know, you're talking to a former computer programmer.
So you're aware of that?
I am aware that nobody is storing images using Fourier transforms holographically. No, they're not doing that.
Holographic? No. What?
Sorry?
Well,
you just introduced Fourier transforms to make a point. That's not relevant because that's not what's being used.
Okay, but you
okay, but nothing.
But you
sorry.
Agree, but you agree. You agreed with what I was saying, right?
I agreed, right, that I knew what Fourier transforms were.
Okay.
And yes, Fourier transforms can be used, right, to make a hologram. Okay, but we're not talking about holograms. The images or the numbers that are being sent back by photographic equipment are stored not holographically, right? They're stored as numbers, straightforward numbers.
And you do realize that you can represent a hologram. In many different ways.
But we're not talking about holograms here. We're talking about, right, supposedly photographic evidence. Okay, these digital cameras are not photographing things with interference patterns. They're photographing, or they're taking light, converting that light, the frequencies involved into numbers. That's it. Frequencies of light into numbers and storing them. That's it. They're not, creating interference patterns and storing that data.
You're right. Like
so your example of holograms is not applicable. You're introducing things just to make a point.
I never said hologram. I was saying how you can use numbers.
Fourier transforms.
Right.
Fourier transforms. That's what you introduced. Not applicable.
What I was saying is you can use numbers and transform a set of numbers into an image.
Indeed. You can put dots on a piece of paper and turn it into an image. Doesn't matter.
Exactly.
What I'm saying is Rob Simon took numbers, data, right, and he said exactly how he did it, and he used those numbers to color an image manually.
No.
I didn't say that, he did. He said, where the numbers were low, I colored it light blue. Where they're a little, where numbers were, well, I said high, I mean, when they're lower, I colored it darker blue. He did that. Do you know what the Mercator map is?
Wait, hold on. I want to address Robert Simmons. So Robert Simmons said he photoshopped Apple's iPhone wallpaper image of Earth. Is that what the image that you're referring to?
So now you're Googling it now, are you?
No, I'm just asking. Is that the image that you're referring to?
No, I can hear you clicking. I can hear you clicking in the background, and now you've obviously got the page up, and you're trying to find something on the page.
No, please answer that question.
Okay, what was the question again?
Is Robert Simmons the guy who photoshopped Apple's iPhone wallpaper image of Earth?
No, the big blue marble, which was used as the Apple wallpaper. Yes.
Okay. That's a fake image.
Hello, that's what I've been telling you.
Yeah, but
It wasn't created for Apple. It wasn't created for Apple. It was created for NASA.
Hold on. You're using that image to debunk the globe Earth? What? Why?
Hello, it was used by Apple, but it was produced for NASA. And they said, this is the Earth, the big blue marble. Now you're just trying you're desperately trying to find something to discredit this idea, right? But the point is, that image was taken to be the updated image of Earth since the last one, which came out in 1972.
Wait, sorry,
right?
I just found some
that was taken as the.
Actually, I was reading misinformation. I have some
we're on
new
Wikipedia now, are we?
I have some new information here, and I can debunk everything you said. So here we go.
Oh, where do you get this new information from?
I'll read it out, and you can either agree or disagree. So, Simon was actually a member of the team which constructed a composite image of Earth in 2002 known as Blue Marble. It's made up from light data collected over a period of 4 months by a satellite, which was then extrapolated into multiple images, which were stuck together and conformed around a digital sphere, with only occasional tiny gaps in the data patched by guesstimated digital touch-ups. That is the explanation I will give you in response to Robert Simmons.
And that explanation goes against what he actually said.
Which was?
He said he took numbers, right? Like numbers like the concentration of phytoplankton. Numbers, yes, not just light data. He was talking about lots of different items of data. Yeah. So
Okay,
that goes against what he said. And
no,
there, you said it was wrapped around a ball. It was wrapped around a ball.
What was?
It's not a photograph. It is a completely CGI'd image because it was wrapped around a ball.
Are you aware of optic fiber?
Fiber optics.
Fiber optics.
Well, I seem to be more aware of it than you.
It's also known as optic fiber, but
Commonly known as fiber optics.
it basically
You're just reading it, you see.
It's basically light that can be transformed into numbers, right? So
Yeah, okay. Where are you going with that?
light data that was captured by satellites, converted into numbers, which were then given to Robert Simmons to then be able to patch up the image of the Earth.
How do you photograph phytoplankton in the sea from a satellite?
You can.
Well, you're not. You take measurements from the sea. Yeah, you can't see phytoplankton because they're tiny.
Okay.
So
No,
you take measurements from the sea, and he was using he literally quoted phytoplankton.
maybe he was being sarcastic or silly.
I don't want to talk about maybe or whatever your opinions might be. He said it.
Okay, what did he say about phytoplankton?
He said where it was high, he colored the sea in light blue. Where it was darker, or lower, he used darker blue. He was telling you how he chose the color palette to paint the sea. He also said about creating or simulating the atmosphere. He also said how he simulated the reflection of the sun on the sea. Simulated, not photographed or used from photographs. He simulated it. He simulated the atmosphere. He simulated the sea. He simulated the clouds.
So you're not going to accept my explanation at all?
No, because it's not your explanation. You just looked it up on bloody Wikipedia.
But it's the consensus. It's the thing that everyone agrees upon.
Not a consensus. It's a mainstream view to try and hide the fact that he let the cat out of the bag.
Look, there is some truth. He did Photoshop some areas, but that's only because there wasn't enough data.
Ooh, okay.
There wasn't enough data.
But again, you listen to the interview. He says how much he simulated. He simulated a lot. He took it all from data. He simulated a lot. He said at the end, well, it's what I think the Earth looks like. I'm not an astronaut. I've never been there. It's what I think it looks like.
You're right. And I agree.
He said that.
I agree with what he said. The problem is you are misunderstanding. So
how can you misunderstand? How can you misunderstand him saying, I don't know what it looks like. I painted it so what I think it looks like.
This is
how do you misunderstand that?
This is the reason why we should not expose this kind of information to the public, because people like yourself are going to take this information and turn it into a conspiracy. There's no conspiracy involved.
I'm not turning into a conspiracy.
Yes,
I'm just telling you what the man said. What the man said. Yeah?
That's not true. And I'm telling
you. It is what you could. Let me go and I'll find it and play it for you if you like.
No. You know what? Go ahead. That would be amazing.
Oh wow. Well, okay, I'll have to find it first, but yeah, no, you can. All right, let me find it for you then. Let's go online and see if I can find it. But well, it sounds like you've never heard it.
I have, but it must have been a while ago. But
oh, right. So you don't remember it like I seem to remember every word, virtually every word he says.
Because I don't need to. I trust the system.
Okay. Blindly trust the system.
Not blindly. You know.
Well, yeah.
No, I don't trust the system blindly,
Okay.
but I trust the system in terms of because it's always produced consistent results.
Cool. Self-consistent results. Okay, no, that's not the. I'm trying to find the video, but for some reason, well, I know what the reason is. All bloody flat Earth videos have been hidden.
Because
So
it's important to discard misinformation.
well, it's not misinformation, right? Okay, here we go. Let's let me see if I can share the screen here. Okay. How was that? Music minimize view. Share screen. Optimize the video clip. Okay, tell me if you see my screen.
Yep, I see it.
Okay, here we go.
Marble 2.0. NASA's Rob Simon made this. And it had wide appeal too. For example, it ended up as the default background on the iPhone.
I didn't even know until I bought an iPhone and turned it on and kind of did a little happy dance.
Simon's job is...
It's primarily taking data and making pictures out of it.
That's what this is. A composite of data sets from several different instruments translated into a picture.
To us, the really cool thing was the data set. Up until that point, there was no realistic color map of the globe anywhere.
So the land layer here comes from
the moderate resolution imaging spectroradiometer aboard Terra.
And the tricky part here was the weather.
So we actually had to take clouds out.
They stashed the clouds for later, went onto the ocean. That came from an instrument that measures phytoplankton in the sea.
Where it was low, I colored it dark blue because they're low mostly in mid-oceans. And then where it's a little bit higher, it was like a little bit brighter green.
Then add the clouds back in.
There's a small problem with it because there's a very slight gap in between each orbit.
So some of those are painted on.
It is photoshopped, but it's has to be.
Then
there was another layer to sort of simulate the atmosphere.
And then there's this little bright spot.
It's called the specular highlight. So it's the reflection of sunlight off of water.
Those are the pieces, but you can't just slap them all together.
It just didn't look realistic.
It looked realistic.
It looks kind of flat, or the clouds are sort of too see-through. So I just hit Command Z a lot.
There's artistry to creating the world.
What I imagine it to be. Unfortunately, I'm not an astronaut. I've never been to space. But I've looked at these images over and over again, trying to sort of get the essence of it. It is photoshopped, but it's has to be. It is photoshopped, but it's has to
be. Okay. There you go. There you go.
Okay. Now that I've heard of
so you're laughing, but everything I've just said, right? You just said, right?
Right.
Okay. So you're laughing at me. This is the guy who works at NASA. He created that image. He explained he did it from data, right? Multiple data sets, right? And then he created the image. He painted it himself, right? He wrapped the image around a ball. He simulated the atmosphere, simulated the specular highlight, put clouds in and made them look like they're above the Earth. And he said, I don't know what it looks like. This is what I think it looks like. I'm not an astronaut. So no, none of these images, right, are real, because when you look at all the pictures from various different sources, they all look different, right? Not only the size and position of the continents, but the colors. You know, the fact that you shouldn't be able to see vivid colors through miles of atmosphere, right? And yeah, on the later ones they've corrected that, but there's lots and lots of images that are just wrong. And yeah, they've admitted that they're all composites. They're all Photoshop. So sorry.
Yeah, I agree. You're right. They are Photoshop.
I can hear a but coming now.
The issue that I have with that statement is just because it's Photoshop doesn't mean that the information isn't accurate or reliable, because the information that was captured through the satellites, I think they're reliable. Sure, there are some areas in the data that haven't been captured properly or accurately, and that's why they had to introduce Photoshop into the image creation process. But at the end of the day, it's still very much a reliable image of the Earth.
They couldn't make the image without Photoshop.
He never
just
said that. He never said that.
No, listen. You can't make that image without Photoshop, because he created that image from data. He simulated a lot of the stuff. If you don't have Photoshop, you can't simulate it, right? So he couldn't create that picture without Photoshop, right? The only one image that NASA claims is a real photograph was the famous one from 1972. And yet we've got footage from the Apollo 11 spacecraft that show them faking an image of Earth from a long distance. So you can't trust that one either. Okay, so no, there aren't any real images from Earth, just artists' impressions from lots of different artists.
Interesting. Artist impressions. That's fine. That's fine. That's all data. You can look at new data of Earth. You can look at the live stream that NASA has on their YouTube channel.
There isn't a live stream. There's not a live 24-hour live stream of Earth.
Okay.
Where is it? Where's the 24-hour live stream of Earth?
Um,
And don't say the ISS, footage, because that isn't live actually, and it doesn't represent the Earth.
okay. I like.
Just send me the link. Send me the link now. I'll get it. If you send it to me on this chat, I'll get it and have a look, because
the live stream of the Earth.
I'd love to see it.
The live stream.
Live stream of the Earth.
Oh yeah, sure.
Yeah.
Let me see if I can find it. Oh, here we go. I've got one here, so I'll send it to you right now. And is there any chance you come back to Globus, or you say
Absolutely not. Absolutely not. I've
Wow.
seen too much. Yeah, I've seen too much.
Well,
You
check it
can.
out.
Here's the thing. You can. I just said,
Are you
right?
laughing at this?
Don't count the ISS, because not only does
Why?
that not represent Earth, right? Because first of all, we're talking about a live stream of the whole Earth. You're showing me this picture, right, which supposedly is from 250 miles up. Yeah. And we've seen it being faked. It's not a live stream at all. Anyway,
Wow.
the point is, right, I've seen too much across multiple different areas. Okay. Now, every time we put something out, bring up a point, yeah, there's usually an ad hoc answer for it, ad hoc scientific answer for it. Oh, it's because of fraction and blah, blah, blah. Yeah. But for every point, there's a different answer. From our side, there's one answer. The Earth is flat. Okay. So on one side, we've got one explanation, and you've got like thousands of explanations for every little part that every little contradiction that we highlight. I go with Occam's razor on this one.
Occam's razor. What? What is?
You don't know what Occam's razor is?
No. What could that possibly be?
The simplest explanation tends to be the truth.
Okay. Oh, well, that's not necessarily true now, is it?
Hello. It's a principle, Occam's razor. Look it up.
If you take that belief and you apply it to every facet of reality, I don't think it's
tends to
applicable.
be the truth.
I don't think it's applicable at all, because basically when you embody that statement, or basically what you're saying is, I'm giving up researching, I'm giving up thinking, I'm giving up researching. That's basically what you're saying.
No, what I'm saying is, in this model, both models here, right,
Yeah.
from
Yeah.
our perspective, look identical. Right, so the heliocentric model and the geocentric model look identical. You cannot tell the difference. There's no experiment that will show you that one is different from the other. Okay.
Okay.
So the simplest explanation tends to be the truth. Right. Now, the simple explanation from our point of view is that our senses tell us that we live on a flat, motionless plane. You go out to the beach, look at the sea, it's totally flat. Okay. You stand still, right? And you don't feel that you're moving at 1,000 miles an hour, right? So your senses are telling you you live on a flat, motionless plane.
Right.
You have to be taught to ignore your senses and believe what other people tell you.
Right.
The simplest explanation tends to be the truth.
Right. But the problem with your senses is that sensors are sometimes deceiving.
But our senses are here so that we can navigate this world accurately. They have to give us the accurate information or we are in danger. Okay.
Okay.
And then,
sure.
Right.
Sure.
So,
well, but then
our senses.
But the problem with that is
our senses.
But the problem. Sorry.
I was just going to say our senses detect acceleration, very, very tiny amounts of acceleration. Right. Now we are hurtling, and I'm just gonna take one of our motions, because we're supposedly in this model hurtling in multiple different directions at once, but I'm just going to ignore all the other directions. I'm going to talk about the one, rotation of the earth at 1,000 miles an hour. Okay. Right. Well, we detect the tiniest bit of acceleration, but we can't detect this this rotation of the earth. Why is that?
I'm not sure. I'm not familiar with that topic. But you're saying that we're able.
Well, you know that we're supposed to be rotating on the surface of this earth at 1,000 miles an hour. You know that, don't you?
Yeah, we see that with the transition of day and night.
Right. So let's do a little thought experiment, shall we?
Sure.
Let's imagine, because the answer, the mainstream answer for why you don't feel that the earth moving is that the earth only moves once around in 24 hours. That's far too slow. Yeah, it does 360 degrees in 24 hours. So that's far too slow for you to feel it. Right. That's the mainstream answer when we bring this one up. Okay.
Okay.
So let's do a little thought experiment.
Sure.
Let's imagine you're on a merry-go-round. Okay. And that merry-go-round is 8 feet across. So you're standing on the edge of this merry-go-round, 8 feet across, and that merry-go-round is going round once every 24 hours. Okay. Now, at the 8 feet across, that merry-go-round will be moving at 3/16 of an inch every minute. So no, you're not even going to detect it. You have to really look closely, and you might detect a slight movement, but you're not going to notice it. Okay. So let's make that merry-go-round a mile across. Now, this mile-wide merry-go-round, right, is now moving at 2.2 inches every minute. Okay, or every second. 2.2 inches a second. So yes, you're gonna notice it moving round very slowly, but you're gonna notice it moving round. Okay. Now let's make that merry-go-round 8,000 miles wide, which is the width of the Earth. Okay. Now that merry-go-round is moving at 1,037 miles an hour. You would be flung off that thing. Okay. Because that's the speed the Earth is going. Right. They make it seem like it's not fast because they're using something called angular rotation. 360 degrees in 24 hours, right? Sounds very slow, but no, in actual fact, it's blazingly fast. To put it in perspective, a lot of people have gone to the fairground and stood on a, what they call the gravitron. So it's a big kind of wheel that you get inside of, and it spins around and you get stuck to the side. You get pinned to the side of the gravitron, right? And this thing spins you upside down and everything. Okay. Now that gravitron is only going at 37 miles an hour, right? And yet you are pinned to the inside wall of that gravitron. If you're trying to cling on to the outside of that gravitron, you wouldn't be able to. And that's only 37 miles an hour. Okay. The Earth is going at 1,030, I think it's 1,037 as well. 1,037 miles an hour. Okay. You'd be flung off that thing. You wouldn't be able to stay on it. Now, according to our senses as well, right? Again, I mentioned our senses register the slightest bit of acceleration. And one of the things that the globe propagandists say is that, well, the Earth is moving around at a constant speed, so you wouldn't feel it. Just like if you're on a train and that train was going at a constant speed, well, while you're in that train, you can do everything. You can juggle balls around and you know, you won't feel any motion whatsoever. The problem is that constant speed in a circle is acceleration in different directions. So yes, you would feel acceleration, just like if you're in a car that's going on in a straight line at a constant speed, you don't feel it. But as soon as that car goes round a bend, again, at that same constant speed, you're going to be flung to one side of the car. Yeah, you would feel it. So no, our senses tell us what's really going on, and our senses are telling us that we are on a flat, motionless plane.
I think our senses are designed specifically for our survival. I don't think they were designed for us to interpret our surroundings in such a magnificent way. Because I believe our senses are designed specifically for, you know, small range activities, for, you know, intimate experiences. I don't think that they were designed to deal
So
with,
you're saying
the extraordinary.
If I was to put you on a roundabout and spun you up at 37 miles an hour,
Yes.
right, so that you were desperately clinging on to stop being flung off, you're saying your senses wouldn't feel that?
No, it would feel it because it's intimate. You know, I'm close to what I'm experiencing, and therefore I experience it. But if we're dealing with something that is much, much, much larger and more, you know,
Still going around at 1,000 miles an hour.
right. What are you trying to say? Are you trying to like replicate the Earth's rotation through a merry-go-round?
Yes,
But
exactly.
the issue with
because
that is, as I mentioned, our senses are designed for close range, intimate experiences. So
Mhm.
you can't.
Well, I've just given you a thought experiment that does that.
Right, but it's not really a thought experiment because I already debunked it.
No, you haven't debunked it.
I
Look,
have. I said that your senses.
as I said, an 8-foot wide merry-go-round, you won't detect that movement. A mile wide, you'll detect it. 8,000 miles wide, you can't help but detect it because you'd be flung off. Okay. The Earth is 8,000 miles wide, moving at the speed of that merry-go-round, which is once every 24 hours, 1,000 miles an hour. Yeah, if the Earth was spinning, as they say it would, we wouldn't be here.
This is where I disagree.
But you're not explaining why you disagree. Why? How does that not? How does my example not apply? If it was simple, you'd have an answer for me, wouldn't you? Or I can hear your clicking, so trying desperately to find something on Wikipedia.
No, not at all.
I'm hearing you clicking. I can hear you clicking away. So you're doing something, you're being very quiet, and I can hear clicking. So you're searching on the web for something to come back with.
No, not at all.
Click.
No. Because I
I just heard another click, I think.
there's, I don't know, like
Click.
I find it really difficult to how do I put it? You can't equate a merry-go-round to the rotation of the Earth because
Yes, you can.
you can. Because a
Why?
merry-go-round, because of the scale and the size of the Earth.
Well, I accounted for that in the experiment, the idea. Yeah.
Okay,
We
but
start
what
with
I'm saying is
8 feet, 1 mile, 4,000 miles.
Okay, but our senses are. I think you might have got me there.
Yes.
Oh, damn it. But I believe that our senses can only detect intimate experiences, even if you attempt to somehow replicate the rotation of the Earth on a smaller scale. I don't believe that that is an accurate representation. I would disagree with that research.
Well, you can't disagree with that because this is our experience. You know, if you go to a fairground, right, you'll find on those like on, let's say, a big merry-go-round with the horses and things, right? The guys who are operating that, they're stood in the middle. Okay, they hardly move, right, because they're just going round, right, in place. As soon as they walk out, they have to hang on to stuff because the further out they get, the more they feel the speed at which the merry-go-round is actually going. Yeah, if they're on the edge, it's the fastest that merry-go-round is going. Close to the axis, it's hardly moving. right? So this is our experience. And I just did the experiment, or the thought experiment, where you have an 8-foot merry-go-round going around once a day, right? That's equates to being very close to the axis on that big merry-go-round. Yeah, so 8 feet across, you won't detect it. A mile across, yes, you start to detect it. 8,000 miles across, the width of the earth, you absolutely would, experience it. There's no way you couldn't experience it. And I think in one of my talks, one of my flat earth talks, I actually give a little demonstration. I show, again, down to earth demonstration of people actually experiencing it. And it's a boat, people in a motorboat. I'll see if I can find it for you, right? Just so, oh, there it is, I think. Let's see, is it this one? Ah, yeah, okay. So bear with me a second. I'm going to share the screen, if that's all right.
Yeah, that's fine.
Okay, share the screen. Tell me when you've got it.
Yep, I've got it.
Yeah. Okay.
Yep.
So little experiment. Okay, here we go. So you can ignore the buffeting, yeah? Motion in straight line. So, do you think their senses detected that?
Yes, because it's intimate. They're very close.
Well,
It's
intimate. It's an intimate. If you're on a merry-go-round a mile wide, yes, you feel the slight motion. If that merry-go-round was 8,000 miles wide, you would feel the 1,000-mile spin of it, and you'd be flung off it, just like they were flung off at, say, maybe 30 mile an hour.
No, you wouldn't. You wouldn't.
Oh, you already, you can't go back on it. You already said I got you there, because your senses would feel it. Yeah, you can't say, oh, I'll feel a pull of, say, 30 miles an hour,
No,
but I won't feel 1,000 miles an hour.
No. What I meant by that was that, yeah, you would feel yourself riding the merry-go-round. You would feel all everything around you and experience the things that you come into contact with and are able to observe. But in terms of how the fastness, or sorry, the acceleration, you won't experience it. You will not be able to.
Okay.
When you're on that merry-go-round,
think of it this way.
Let me finish. When you're on that merry-go-round, it feels like you're not going anywhere, and it feels like you're just in one position. But yeah, everything is moving, but
Oh,
it
you know,
seems like it's
no, sorry, mate. No. If you're on a merry-go-round, you feel the motion round, yeah? Even though it's going slowly.
Not if it's on the scale of the earth, you wouldn't even know that you're moving. It would,
Okay.
like,
Wait a second. Imagine that 8,000 mile wide merry-go-round, right? And you are in the center. Okay, you're in the center of that merry-go-round. It's moving at 1,000 miles an hour on the edge. In the center, you wouldn't detect any motion, because, you know, literally you would turn around. If you're standing right on the axis, you turn around once every 24 hours. Okay, if you started walking towards the edge and you got 8 feet away from the center, as I said, again, you wouldn't feel very much motion. You'd notice, 3/16 of an inch every minute. Okay, you keep walking right out towards the edge, right? You get a mile away, half a mile away from the center. Okay, now you're moving at 2.2 inches a second. So yes, it's a slow motion, but you're still moving. Okay, you detect that, you feel that. If you keep walking out to the edge, right? This is the same experience. Yeah. You keep walking out to the edge, you're going to feel a faster and faster motion, a faster push off that merry-go-round until you get to the edge, and now it's spinning at 1,000 miles an hour. You won't be able to hang on no matter what. Okay. So no, it's not, you don't have this kind of, oh, you feel slow motions, but you can't feel 1,000 miles an hour. No, right? You'd feel it.
In your vicinity, but not, no, you won't. It won't. It will feel like.
Are you disagreeing with me that on that spinning system, 8,000 miles wide, if you start at the center, you won't notice any movement, and the more you go out, the faster movement you will notice. Yeah, you're disagreeing with that, are you?
I'm saying if you go further out, it will.
Are you disagreeing with me?
Yes.
You're disagreeing with me.
Yes.
So you're disagreeing with common experience that on a spinning system, in the center, it's the slowest motion. You're not going anywhere because you're just turning around. Yeah. And the further out you get, the more you notice the, a force that's throwing you off, throwing you out. I think it's a centrifugal force. You're saying that doesn't exist, are you?
I'm saying the further you go out, it will feel like you're not moving, but you're moving.
But that's only in the center. If you're in the center of a spinning object, yeah, that merry-go-round, you're not moving. You're just turning around on the spot. But as soon as you walk away from that center, now you're moving around that center. All right. The further out you get, the faster that motion around the center gets. Okay. And that is common experience.
Not necessarily.
Right? What do you mean not necessarily?
Not necessarily, because
as I said, go to a fairground and watch what happens to the guy who's operating it, and he stands in the center. He's there not moving as far as the spinning system's going. You're sitting on your horse on the edge and you look towards the guy in the middle, he's not moving. Okay. But you feel you're moving. You feel like you're, if you fall off the horse, you'll end up on the pavement. You won't be, you'll be flung off that. You'll, if you're not holding on. Right?
When you're on
it's centrifugal force. Okay.
Right.
So
when you're on a
centrifugal force.
When you're on a train,
yeah.
Are you moving? Are you stationary?
I think I addressed this as well. Yes, at a constant speed, you do not feel like you're moving. So where are you going with that?
Have you experienced a train moving at a rapid pace?
Yes.
Did you feel any difference?
As I said, a train moving at a constant speed. No, you don't feel.
No. Did you feel any?
Okay, all right. Okay, when the train starts accelerating, yes, I feel it. When the train is moving at constant speed, sorry?
If you were in a enclosed capsule that completely removed you from getting into contact with space around you, and you were moving at a very rapid pace, it would feel as if you were not moving and everything else is moving. And that
okay, you're saying a rapid pace makes a difference. No,
that is what the Earth is. The Earth is like a capsule. The atmosphere.
Wait. I know what you're trying to say. I've already addressed this. Okay. If I was in a closed box inside a train, I couldn't see out the windows. If that train pulled away, I'd feel the acceleration. As soon as that train reached a constant speed, no, I wouldn't feel anything. If it's going in a straight line at a constant speed, I wouldn't know I was moving. Okay. But if that train started going around a curve, I'd be thrown to the outside edge of that box. because most constant speed in a circle is acceleration in different directions. So you do feel acceleration, you know, outwards or being flung off, you know, it's the outwards, because if there was no wall there, I'd be flung out of that box. Yeah.
Okay.
I'd be pinned to the wall. Okay. Constant speed in a circle is acceleration. You feel acceleration.
Wow. Wow.
What do you mean, wow?
You haven't proved anything, but you know what? That's okay.
Okay, let me prove it to you then. Let me
Sure.
prove it to you, because I can actually show you. Oh, is it this one? Oh no, it's not this one. Oh, kids guide. That's sorry, I opened the wrong thing. Give me
That's
a
okay.
second. Complete guide. Yeah, so I actually, when I actually started looking at this, I just went on to find out what the equation was for you know, to describe this. And if you bear with me a moment, let's see if I share this screen. Hold on a sec. Oh, it's not there. Sorry, bear with me. It's
That's
still
all good.
loading. Sorry.
That's all good.
Yeah. I've just got to find it. It's so yeah, I was looking for the equation that explained it. Okay, constant speed. Ah, there it is. Okay, so slideshow. Okay, so let's do. Oh, okay, where is it? Oh, I can't find it now. Okay, I'm gonna have to. Sorry, try it this way. Okay, share screen. Stop that. Share screen. Ah, there it is. Okay, tell me when you see the screen.
Yep, I see it. Basic math.
Right, yes. Uniform circular motion. Yeah.
Yes.
So read it with me. Uniform circular motion can be described as a motion of an object in a circle at constant speed. An object moving in a circle is accelerating. The acceleration, the calculation is AC equals V squared over R. That is telling you the acceleration. And yes, we sense acceleration. Doesn't matter that we're moving at constant speed. It's constant speed in a circle.
No.
Oh, so the Earth is not rotating in a circle. Is that what you're saying?
It is, but
Oh, it is. Okay, so is it moving at a constant speed?
yes.
So what part of an object moving in a circle is accelerating, don't you get?
Scale, size, magnitude.
Where does it say anything about scale or size? In fact, it does say scale or size. R, radius, okay, which means the bigger the radius, the faster acceleration.
Right.
Right.
I agree with it.
Thank you.
But that doesn't
So
mean
let's
anything.
move on. It does. It means that we would feel acceleration on standing on a spinning object like the Earth,
No, we
right, which is
wouldn't.
8,000 miles wide, spinning at 1,000 miles an hour.
Yes, you would feel it if you were relative to
Hello,
the
look,
size
look,
of the Earth.
look. It's showing you here, right? you're that thing here, you're being accelerated that way, and then that way, and then that way, and then that way, and so on. You would feel the acceleration. An object moving in a circle is accelerating. We sense acceleration, the tiniest bit of acceleration. If a car moves from stationary to 1 mile an hour, we will feel it. And you're trying to say we do not feel an acceleration, right? Which is, you know, which arises from a 1,000 mile an hour spin of the Earth. No, you're wrong.
We don't feel it. We don't. There are two reasons why we don't feel it. We don't feel it because of the size, and scale, and magnitude of the Earth, and the fact that we're tiny little things.
And I've explained, right?
Anything.
I've explained. Secondly, yes, we would if.
Secondly, gravity is putting a hold on us from having experienced any kind of circular motion.
Can you see this?
Sure.
Have you been on one of these?
Yes.
Right. The gravitron is spinning at 37 miles an hour. Okay. You are being pinned to the inside wall of this. You could stand up on the inside wall of that. Okay.
Right.
Gravity is not going to pull you down to the ground. Yeah. You are pinned to the outside, the inside wall of that. If that wall was to suddenly disappear, you would be flung off into the air, right? And you probably wouldn't survive it. Okay.
Okay.
Do you agree?
What's your point? Sure.
Do you agree?
Sure.
Huh?
Sure.
Okay. Now scale that gravitron up to 8,000 miles wide, right? And going at 1,000 miles an hour. Okay. The same thing would occur. You'd be a smear on the inside of that wall at 1,000 miles an hour. But if you survived, let's say, if you're able to survive that speed and that suddenly the wall disappeared, you would be flung off, wouldn't you?
Can you do an experiment for this? Can you get, I know there's software out there where you can create models.
Oh, for crying out loud.
Why don't you do that?
For crying out loud. I cannot make a merry-go-round 8,000 miles wide.
No, I'm not talking about in real life. Using a computer program, I'm sure you'll be able to accomplish.
Are you disagreeing with anything I said about what would happen?
Yes.
So let's imagine this gravitron here, yeah? If there was somebody standing in the middle of that gravitron, right, they wouldn't be flung out into space. They'd just be turning around in a circle, wouldn't they? Is that right?
Mm-hmm.
Sorry?
No.
Is that right?
No.
So the person standing right on the axis of that spin, right, would he be just turning around in place, or would he be flung off to the middle? Flung off to the edge, sorry. Which one? Is he stuck in the middle, turning around in place, or is he being flung to the side?
They'll be flung to the side.
Let's make it simpler then, because you can't grasp this. Okay, merry-go-round. Okay, if somebody's standing on this merry-go-round, right, and the merry-go-round is going round at let's ignore the numbers down here. Let's imagine this merry-go-round is going around at 37 miles an hour. Okay, the person on the edge here is going to feel that motion. He's going to have to hang on because it's going around at 37 miles an hour. Yeah. But the person standing on this middle point, on this post, all he's doing is spinning around in place. Is that right?
But the thing is, there is a force.
Answer the question, yes or no.
What I'm saying is that there is a force, okay? There's a force.
On that person standing in the middle, is there any force on him? is there any force on that person standing right on the axis of spin? Is there any forces acting on him?
Yeah, gravity.
Forget gravity. We're talking about the spinning platform. Is there a force flinging him to the outside?
You're right. I agree.
Yes or no?
I agree. I personally experienced this. I realized that as I put my body towards the center,
Right.
I was less likely to shoot off.
Okay.
As I
So
put my
so
body
now
onto
you
the
can
outer
also
edges, then yes, I would most likely.
so now also you can also agree that if he went from the middle and started walking to the outside, he'd feel a stronger and stronger push off the merry-go-round. Yeah. The further out he gets, the faster he's spinning round, and the more there's a force trying to throw him off the merry-go-round. Is that right?
The problem with this.
Is that right?
Yes.
Is that right? Yes or no?
Yes. Yes.
Right. So if that merry-go-round was wide enough, yeah, if it was 8,000 miles wide, yeah, 8,000 miles wide, and he went to the outside, now it's going at 1,037 miles an hour, he won't be able to hang on.
Sure.
Is that right?
Yes.
Huh?
Yes.
Yes. The Earth is 8,000 miles wide. It is going around at 1,037 miles an hour. If that was true, we wouldn't be able to stay on the Earth. We'll be flung off. Gravity is not strong enough to guard against or prevent somebody being flung off at that speed.
Okay.
So let me stop sharing now.
Okay, the problem with that is
You're so desperate to find a problem with that.
no. The problem with that is you're not taking into account the force that's keeping you from shooting off.
What force keeping you from falling off?
I'll give you an example. So the fairground ride, right? The force is exerted by the walls of the chamber that's stopping you passing through them. Would you agree?
Right. Yes.
Right. This is called a reaction force. Now, on the Earth, this is known as gravity. Gravity is pulling you down, keeping you from shooting off. Does that make sense?
Okay, but here's the gravity. Oh, let me go back to sharing the screen again. Okay, hold on. So here's the gravitron again. Can you see that? You see that?
Yes.
Right. So there's a version of the gravitron, right? I've been on several like this, that doesn't just spin like that, but it also starts tipping upwards. So it's now 90 degrees to the ground. Okay. I've been on that a few times. Okay. Now, right, you've got gravity pulling you down, because now this gravitron is spinning 90 degrees to the ground. Okay. When you are, say you are on the upward slight slope of the or the upward spin of the gravitron, right? So you're directly above the ground, but at the highest point of that spin, yeah.
Yes.
Gravity is pulling you down, but if that wall disappeared, you'd fly off. right? Gravity will not have an effect on stopping you from flying upwards before then it will, will start to drag you down again. But you'll be flung upwards first. Again, that's 37 miles an hour. 37 miles an hour. Yeah. It's not going, even that isn't enough, or gravity is enough to stop you being flung off at 37 miles an hour. Right? We're talking about 1,037 miles an hour. Right? If there was no wall there, because we're talking about people standing on the outside edge of that gravitron, okay, you would be flung off. There's no way you'd be able to stay on there. Right? Gravity will not have an effect. It's not strong enough to stop you being flung off at that speed.
It is.
No, it's not. As I said, do that on a gravitron that turns up on 90 degrees. You'd still be stuck to the wall. You'd still be stuck to the wall even when you're at the highest point of that gravitron. Yeah, still stuck to the wall. You don't fall off it. As soon as you go up to the top, you don't fall down. No, you're being held there by the centrifugal force that's flinging you out. So if you take that wall away, you'd be flung out, for maybe 100 yards before you start falling down again. Yeah, gravity isn't enough to stop you from doing that. Obviously, depending on the speed you're going out, right, you'll go either higher up or you come down earlier. But we're talking about 37 miles an hour. You'll go at least 100 yards. You have 1,000 miles an hour. You're not coming back.
Okay. The problem.
There's no problem. The problem is you just don't want to accept stuff even when it's right in front of you.
I'll explain it. So, are you aware of Newton's first law?
Yep.
So, an object in motion stays in motion at the same speed and in the same direction. Would you agree?
Yep.
Right. So the Earth, due to its magnitude, the Earth is large enough that standing on its rapidly rotating surface feels like you're standing still, because you're mostly moving in a straight line. Does that make sense?
No, you're not. No, you're not.
Wow.
Again,
Wow.
again, uniform circular motion. It's
I
not a straight
agree.
line.
I agree.
No, you just said a straight line. No, you said we are moving in a straight line. No, we're moving.
No.
We would be moving in a circle, which is uniform circular motion.
Let me explain.
Which means acceleration in different
explain.
directions. As you said, if that force was removed, you'd go off in the same direction at the same speed.
I'll give you an example.
But the direction is changing constantly. Right? So it's acceleration.
I'll give you an example.
You're arguing against this.
No. I'll give you
You're
an
arguing
example.
against this.
I'll give you an example. So imagine
All right, give me an
being
example.
in a car, right? And you feel the force
Yes.
and you feel the force to the side when the car turns, right? So when you're in a car and you turn to the left or to the right, you feel the force, right? You're being pushed in the other direction.
Yep.
Now, imagine that car is moving very fast. I'm not sure what the velocity rate is for the Earth, but I think you mentioned 1,000 miles per hour. Is that right?
Okay.
But
yeah.
anyways, imagine the car is moving very fast, right? But it takes 6 hours. 6 hours to turn left. Now, would you feel the supposed centrifugal force that you're talking about? You wouldn't. Why? It's because
yes, you would.
no. Let me finish.
It's because it takes 6 hours for you to turn left, right?
It
6
doesn't
hours.
matter.
Which means, wait, let me finish. Which means that the turn is slow enough that the lifting force, right, in the case of the Earth, or the sideways force in the car taking the 6 hour turn is barely noticed. You don't notice this lifting force, this force that is supposedly supposed to throw you out. You don't feel it because of because of time. You haven't taken into account time. It takes 6 hours to turn left. So you're not going to feel it.
And you are performing a fallacy, appealing to incredulity, because we can't experience the scale that you're talking about. Okay, when you scale down, right? Wait a minute. I listen to you, so listen to me. If you scale down the Earth's motion to the scale of a car, yes, you would still feel, as soon as that car starts to turn, right, you would feel the push sideways. It'll be a small push at the speeds that a car makes. Wait, it'll be a small push at the speed cars travel at. But when you scale that up, right, keeping the same scale, right, but keeping the same percentages, yeah, so everything matches, you know, so it's the same as like being on that merry-go-round, yeah. So we've got the 8,000 mile wide merry-go-round. The car is at you know, sort of a mile away from the center, yeah. Now again, 2.2 inches per second, right, is a speed. 2.2 inches a second, right. The push sideways is going to be very, very slight. You move that car out so it's moving faster, yeah, that push is going to increase until you get to the outside of that merry-go-round where you're going now at 1,000 miles an hour. That push is going to be massive. You're just appealing to the fact that we can't imagine the scale because, you know, we don't live at that scale. Yeah, you're just appealing to incredulity.
I disagree, because this is a well.
You can disagree, but you haven't got anything to back up your disagreement.
I'll explain. It takes 6 hours to turn 90 degrees on Earth.
I know, but it doesn't matter. You feel it if you go around a very, very gentle bend in a car that's only going 50, 60, 70 miles an hour. You feel that. Okay, even if it would take, when you say 6 hours to turn left, what do you mean by that? If I turned left in a space of like 10 meters or a meter in 6 hours, yes, I'm going to feel it. You know, you feel acceleration. We feel acceleration, no matter how small. Our senses, you know, need to be able to detect acceleration. Otherwise, we won't be able to stand up straight.
That's not true at all. Like, what you're doing
It is true. You've got accelerometers that tell you, like, making micro movements every moment you're standing up straight. As soon as you feel an acceleration to one side, you instantly compensate with your muscles without knowing it. That's why we've got the middle ear, you know, to tell us if we accelerate in any direction. We've got senses that detect the minutest.
One more time, and if you refuse to accept it, then you know what, we have to move on to a different topic. It takes 6 hours. 6 hours to turn 90 degrees. From our perspective.
I understand.
Okay,
no,
so
I understand what you're trying to say.
Go back to that image. Yep, click on that image, or the smaller one.
Oh, let's go.
The small people, and imagine if it took 6 hours for that tiny movement to the left. 6 hours to turn 90 degrees. Do you think that these people that we're looking at here will be fleeing off? No, they won't.
Yes, and I'll tell you why. Yeah,
Oh
because
my
this is
God.
listen,
Oh my
listen,
God.
because you missed it the first time. You obviously missed it the first time. Yeah. When I showed you this image of the 8 foot across, yeah, it was taking 24 hours to go round once. Okay. 24 hours to go round once. No, at that size, you wouldn't feel it. In this image, when you were it's a mile across, it's still taking 24 hours to go all the way around. But now at 2.2 inches a second, you'll start to feel it. You'll start to notice it. At 8,000 miles, you're still going at, once round in 24 hours. But now the speed at the edge is 1,037 miles an hour. Of course you'd feel that. Okay. You're saying you wouldn't feel it of 6 hours. I'm saying you're going to feel it in 24 hours. You're just missing it because you don't want to
No,
accept it.
that's not how it works.
It is how it works. I'm showing it to you right there.
Nice try, but that's not how it works.
I'm showing it to you right here.
No,
If you can't say, oh, for crying out, what is different between this model and the model of the Earth?
You know
When I say 8,000 miles across,
you know exactly
what?
Right.
No, sorry, no, explain to me, because this roundabout is the width of the Earth, okay, and it's going round once every 24 hours. And because of the size of it, right, for it to go once around every 24 hours, on the edge here, it has to go at 1,037 miles an hour.
No, you're being very
That's it.
No.
And if you start walking in, from the edge here, you'll get to the middle and it's not moving at all. You'll just be, if you're right in the middle, standing on this post, all you're going to do is turn around once every 24 hours. You're just appealing to incredulity because you can't imagine the scale of it. As I said, if you go from that point in the middle where you're turning around once every 24 hours and not actually moving anywhere, and you start walking out to the edge, you'll feel a faster and faster movement around and a push outwards, which is centrifugal force.
Okay, I want you to picture yourself on that merry-go-round. And as it's doing 90 degrees, it's gonna take 6 hours. Okay.
I'm telling you, it's going around in 24 hours.
Let me explain myself. During that entire time, you're jumping up and down, you're running around, you're going all over the place. What I'm saying is there's so much time involved that it's unnoticeable. It really is. It really is unnoticeable. And you're not doing justice by putting these figures on this thing. You need to make them tiny. I'm talking barely noticeable.
I know. I couldn't make it. I wanted to show people flinging off it. That's the thing.
Now, if you put these humans, barely noticeable, there is no effect. You will not notice the Earth moving at all because of its magnitude and the fact that it takes 6 hours to do 90 degrees.
At what point does it reverse? At what point? At what point does it reverse? Yeah, because again, going back to it, at 8 feet, it's going at 3/16 of an inch, a minute, right? You make it wider, you go out further, right? It's now 2.2 inches a second, right? At what point does it stop increasing and then start going so you don't notice it? At what point? At what size does it start reversing? Explain to me. Give me the maths for that.
It's not reversing. What it turns.
It is reversing because you're saying, right, that you won't notice it, just like you wouldn't notice it standing in the middle, yeah, and going out, you know, a mile, you'll just barely notice it, right? But the further out you get, the faster it will go, and the more you'll notice it. Yeah. So at what point does it stop increasing and then start decreasing so you don't notice it anymore?
Are you aware of this effect? Are you aware of car rims?
I wish I'd started recording this. This is incredible. Sorry, am I aware of what?
Car rims.
Car rims.
Yes. So the rims of the car.
Yeah.
Right. If you look at a spinning wheel and it had a rim on it, right? When it's slowly accelerating, you can see the wheel turning, right? You can see the rim turning as well. But when you get to a point in acceleration, when it's going really, 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 really fast, the rim of the wheel appears as if it's not even moving at all. Even though the wheel is moving super fast, the rim,
you can't see it because it's moving fast.
The rim appears as though it's stationary.
No, it doesn't.
Yes.
It's blurred. You can't see it. It's going fast.
YouTube it, Google it, the phenomena. And this is what I'm saying. I'm saying, yeah, you're right. There is a point where
I'm sorry. I can't believe this. Look, don't you know that there's a refresh rate on a camera? And then those times when the wheel is spinning at the refresh rate, the wheel looks like it's not moving. It's the refresh rate of the camera.
No,
for crying out loud.
It's not the camera, it's your own vision, your own senses that you keep talking
no
about. And you're saying
the camera takes images.
Our senses are this, our senses are that.
The camera takes images at a certain speed.
No, I'm not talking
the camera takes images at a certain speed. When that speed matches with the speed of the wheel going round, it will appear to stay still. If it goes a bit faster, then the wheel will appear to go backwards.
And that's what I'm saying about this phenomenon.
The wheel will appear to go backwards. The wheel will appear to go backwards when you get a little faster. Does that mean the wheel is actually going backwards?
Let me finish.
No, I'm asking you now, because you're saying that you know, you look at that wheel and it looks like it's standing still. Right, but if you go a little faster, that wheel will look like it's going backwards. Does that mean the wheel is actually going backwards?
No.
No, it's an effect. It's an optical illusion caused by the refresh rate of the camera. For crying out loud.
I'm not talking about a camera, I'm talking about your own eyes, but you know what, if you don't want to...
You don't see it with your own eyes, you just see a blur.
Hey, look. All I'm saying is...
No, for crying out loud. Yes, you don't see with your naked eye, right? When a wheel goes around really, really fast, you don't see that wheel appear to be stationary. It only appears when you view it through a camera.
None of these demonstrations are scientific at all. Also,
now you're arguing, you're desperately arguing against the truth here.
I'm going to conclude with one thing before I move on to the next topic. 6 hours.
Well, I think
to turn 90-degree angle.
And I'm saying 24 hours to turn 360 degrees.
That's all I have to say.
24 hours to turn 360 degrees. And yet, as I said, yeah, you would be going at 1,037 miles an hour.
Okay,
sorry,
I'm
it's
saying
it's maths.
Okay, what I'm saying is, even if you went 1,037 miles per hour, it's still going to take 6 hours for it to do 90 degrees.
I know, but in that 6 hours, you would have to move over 6,000 miles in that 6 hours. 6,000 miles in that 6 hours, which equates to 1,000 miles an hour, which equates to 1,500 feet per second. 1,500 feet per second. Every second, you'll go over 1.5 kilometers every second. You're saying you're not going to feel that?
Not at all.
Okay, right, fair enough. Yeah, I can't. I don't know what to say.
Just like if you were in a car and you were, turning left, but it took 6 hours to turn left. That's exactly the same phenomena, and you won't even realize that you won't even sense
Okay, if that car was going at 1,000 miles an hour, and it's you were going 6,000 miles in that 6 hours, yeah, and you were turning to the left, yes, you would feel it. It's just that you can't imagine the scale, so obviously it can't be true.
No. You haven't. No, I'm saying if you were in a car and you were going at 1,000 miles per hour, and you made a left turn, it will take 6 hours to turn 90 degrees. It will take 6 hours to turn left.
Yes, and in that 6 hours, you'd go over 6,000 miles in that 6 hours.
Oh my God. No.
And yes, you would feel it.
That's not how it works. Oh, Jesus.
Well, yes, it is.
Oh my God.
If you're going 1,000 miles an hour, after 6 hours, you go 6,000 miles.
I really want to move on to a different topic, but
perhaps my math is wrong.
your math is definitely wrong.
I wish I'd recorded this. Sorry.
Your math it is recording on my end, but your math is definitely wrong.
Okay. Please send me that recording.
I'll definitely post it on YouTube and everything. So the problem with that is
okay.
It's I'm not going to move on to this, but I really want to talk about another interesting topic that you talk about.
Can we close it off soon, because we've been on here for 3 hours now? Yeah.
Oh, has it? Oh, okay.
Yes.
Do you want to end it there, or how long do you have left?
Well, probably because we've been here for 3 hours, and this is getting quite laughable, and on both sides. I'm sure you're laughing at me, but this is getting quite funny.
Sure, but how long do you want to end it here now, or?
Well, if you've got something snappy to wrap it up with, then great. But I've been here for really 3 hours, and I've got stuff to do as well.
Okay, I understand. I was really hoping to get into a little bit of history and the Hebrew Israelites, but maybe another time.
Maybe.
Cool. Well, I guess we can wrap it there.
Okay.
Look, I've given my take on everything. I gave all the evidences, and these aren't mainstream evidences. This is evidences that everyone accepts. That doesn't make it mainstream, and everyone accepts it.
Except it was evidences I could actually hear you clicking through to Google or Wikipedia or something.
Not at all. And I disagree with that statement. Just for record. Right. Look, I think everything you shared is just elementary. I don't think you've actually gone any further than surface level. I mean, the math that you're demonstrating here is like basic mathematics, and I don't think you've looked at.
Yes.
I don't think you've looked at all the variants that are involved with this particular math. There are different.
Yes, I have.
There are complications.
Velocity, acceleration, radius.
There are certain.
That's all. They're all the elements.
Okay, but you do realize that in physics you have variance, which means that just because
these are the variables.
Right,
these are the variables.
What I'm trying to say is that there are some phenomena that take these variables and say, you know what, they don't apply during this particular circumstance.
Okay, so what are they? What are they? What are the variables that apply to this?
Investigate that.
You need
No,
to
no,
take
you
the
tell
time to-
me. Tell me, what are the variables
I'm
that
not going to,
change
because you
this?
said you don't have time, so I'll have to wrap it up.
Okay, all right.
But I
You
want
just
you to
say
actually
such
investigate it
ridiculous
further.
things, sir.
No. I think I think you have confirmation bias, and it's
All I've heard from you, sir, is confirmation bias. You're desperately trying to find things to disagree with me on, and when I get you to agree, you then go, "Oh no, well I've changed my mind now." It's like everything you've said so far is confirmation bias on your side.
no. I think you have an agenda, and
I
I'm not
do.
sure-
I know the Earth is flat. I think you have the agenda.
No, I think you honestly have an agenda, and I'm not sure what that agenda
Yes,
is.
the Earth is flat.
No. Your agenda is something else.
So you
Your
don't
agenda-
have an agenda. You
your
don't have
agenda-
an agenda then.
Your agenda is to basically, I'm not sure what happened, but you have this agenda of, this place disagree with the scientific community. I'm gonna come up with alternative.
No,
evidence to
all
say
I
that's
did-
not scientific.
All I did
No,
was
no.
all I did was look at the world, right, that they presented to
You
me,
are
and then
sharing-
tested it. I
You are
tested it.
sharing misinformation.
No, I'm not.
Haven't conducted
you who are
any
sharing
small
misinformation.
experiments, and it's look, Dave. I used to.
I've
be,
been all around the world doing experiments, mate.
Dave. Look, I used to be a flat earther as well. Okay.
No, you didn't.
Yes. I used to be a. flat
No,
earther.
you
How
didn't.
old are
I've
you?
never heard of you. Where's your
Yeah.
experiments? Where are your videos that you've shown?
I
Showing your
haven't
proof.
made any videos. I'm just.
Oh, so how are you a flat earther? How are
because
you a
I'm-
flat earther?
Because I'm
If
one
you
of the-
if you're disagreeing with all the things I'm saying.
No, because I realized that I was a period in my life where I just wanted to believe it in something, and I wanted
Well,
to
your
go
mental
against
illness
the
isn't my
system, the
concern.
brain and the usual, and I wanted to just stand down and be different. And I became a flat earther.
Your mental
started-
illness is not my concern, nor does it relate to
No,
anything
and
that
I-
I'm
and I-
doing.
And I started to believe in alternative medicine and alternative research and alternative this and alternative that. And what I'm trying to say is I snapped out of it. I realized I was wrong. I realized the information and the sources were wrong.
Well,
And
good
I
for
would
good for
highly
you.
encourage-
Well, good for you, right? But you know what? When I looked at alternative medicine, not only did I heal myself, but I healed my mother and got her out of a wheelchair. And I spent the last 9 years helping other people heal themselves with spectacular results, even after the medical system has said, no, we can't do anything more for you. Yeah. So, you know what? It's all very well talking about the flat earth where you can't actually go and, look out into space and whatever. But when you're talking about things here on earth that we can have measurable results, you know nothing, mate. Honestly.
Wow. That's incredibly low. And I think it's important. I highly encourage that, you maybe reach out and come back and come to your senses, like you mentioned earlier.
You can drop the condescending attitude, mate, because I'm not like somebody desperately seeking attention or anything, right? It's like I am looking for the truth here, and like I am finding the truth, and you are acting as a gatekeeper, to try and keep the status quo. I don't know what happened to you, but are you being paid to do this?
Like you, Dave. Are
you being paid to do this?
No, not at all.
Okay. Well, I'd love to see what sort of videos you put on your channel.
But all I have to say is, I used to be just like you.
No, you didn't. No, you didn't. You're nothing like me. I can tell that.
I would highly encourage that, maybe reach out, maybe think about what the things that you're saying and doing. Maybe
what you're misunderstanding is we have thought about, not only thought about it, done experiments, tested it, real world experiments.
But have you
As I
read
said,
the
I've been all
Bible?
over the world doing experiments, testing what we've been told, and what we've been told isn't true.
So there is
So
absolutely
nothing you've said today has stood up to any scrutiny whatsoever.
because you have confirmation bias.
No, I showed you why it doesn't stand up, and you've just
No.
gone, well, I disagree, or, oh, let's agree to disagree, or let's move on, let's not talk about it anymore.
No, the only
That's
reason why I
confirmation
said
bias.
that- the only reason why I said I wanted to move on with the conversation is because it's clear you have confirmation bias, and that no matter what I tell you, you will come back with something and say, I disagree, or this is wrong.
No, I'm not coming back with stuff. You've been coming back. I'm showing you what I've learned. I haven't kept adding stuff to it. I've been telling you what I've learned. You just keep coming up with stuff to try and debunk. That's all you've been doing.
I understand that you have a dislike of the system, and I understand that, but the science and
That dislike of the system came about by finding out it's fraudulent, by finding out things like this.
this isn't fraudulent. This is truth.
How do you know?
How do I know? Because I trust the system and I trust the entities involved in the system. I trust that.
So if a con man
telling me
is
the
telling you stuff, you're just going to keep trusting that con man, even if you find out that con man just lied to you about something, you're just going to keep on trusting the con man, are you?
Yeah, it's in our human nature, right? Because in our human nature, it's best that we follow what others are doing. Otherwise, if we end up.
Okay, so you're saying be a sheep and follow what anybody tells you.
No,
don't ask
no,
questions.
that's not what I'm saying. What I'm
No,
saying.
you just said it. Our human
what
nature,
I'm
we have
saying
to
is
follow.
If you stray from the path and you end up on some alternative path, that alternative path will most likely cause a lot of issues in your life. It's better that
Caused a lot of issues in my life.
if you decide to go down that road.
Yeah, and I accept that.
So
So now what?
it's better that you stay with the group.
Better for who?
Maybe the group may say things or do things that you may disagree with.
Better for who?
But it's best that you do that.
Better for who?
Better for you, better for everyone.
Well, no, I decide what's better for me, and I've decided on this path. So better
But
for who?
But that's you being selfish, if you understand what I mean.
Selfish.
Yeah.
Selfish. No, I'm okay. Well,
Because
okay,
what
yes,
you-
in a way, you're right. I am finding things out for myself. Yeah. And I'm putting out what I find, right, for anyone else who wants to listen. Right. I'm not telling anyone they have to believe me. I'm putting it out there and saying, go and look for yourself. Right. We're not saying you have to believe me. This is what you're saying to me. You're saying you have to believe the system. You have to believe what you're told. Right. No, I'm saying no, I refuse to do that. I have found things that do not match what they've told me, and I'm going to find the truth. And you know what? I have found the truth.
What if
I found the truth about all this.
What if you're wrong?
This,
What if everything you
the
thought,
way the earth is.
What if everything you knew was completely wrong?
What if everything you knew was completely wrong?
No. Then what?
Then what?
The thing
What
is,
if you knew? What if you
knew-
found out that everything you knew was completely wrong?
Okay,
Then
if
what?
Everything I knew.
What
was
would you
completely-
do?
if
What
everything-
would you do?
Let me explain. If everything I knew was completely
No, what would you do?
Let me explain. If everything I knew was completely wrong, it would be the scientific community to come out and say, hey guys, we got it all wrong. And then I will follow the scientific.
Oh, are you saying you're the scientific community?
No, I'm not
So-
saying I'm the scientific community. if the scientific community came out and said, "Hey, you guys, look, we got it all wrong. The Earth is flat," and
Oh, then you would
everyone-
follow
and then
because you're a
everyone else is
follower.
gonna follow. Yeah, but I'm not going to.
Okay, I'm not a follower, I'm afraid. I'm not a follower. If somebody tells me something, I'm going to look at it first and decide for myself. Right? If you want to be a follower,
Sure, if you
that's
have the
up to you.
time,
And great, enjoy yourself being a follower.
if I
But
had
that's
your
not
time,
me.
then yeah, I
That's
would
not
do
me.
that
I'm
as
going to
well.
ask questions.
If I had your time, I would do that as well. But for the most of us, we have other commitments and responsibilities that prevent us from,
Is that another slight passive aggressive dig? Is that
No,
if
no,
I
no,
had
no.
your time, for crying out loud?
No,
Okay,
no.
I think that's the end. I think that's the end of this talk, because there's absolutely nothing to be gained, right, from this. You've all you're trying to do.
So you came in here to gain something?
What? But are you saying that you instigated this just so that neither of us can gain anything?
No, not at all. But like, I obviously just want.
Right. So why did you ask that question then? For crying out loud! Again, you're trying to paint a picture here, right? To again, support your view of the world, that anyone who doesn't go along and follow the mainstream must be some kind of desperate, mentally ill person who needs attention, needs to differentiate himself from the crowd. No, that's not the truth. Yeah, it's not the truth. We are not followers. If you want to be a follower, great. Follow to your heart's content, right? Just go and do it somewhere else, mate.
Look, all I have to say, all I said was I used to be like you.
No, you didn't.
And I came out of it, and it was amazing when I finally did and came to my senses.
No, you were nothing like me. Everything that you've been saying today has demonstrated, right, without a doubt, that you and me are very, very, very different. And we've never really been the same, except for before I woke up to all this. And yes, I might have been very much like you, in the system, go working 9 to 5, doing everything that I've been told to do. Right, but
No,
as soon as I changed, as soon as I woke up, that's where the similarity ended.
No, I used to be just like you. I thought I was woke.
No, you didn't.
And I believed in flat Earth, and I believed in all.
I don't think I'm woke.
Things. Then I realized, something was not right. If I'm on a path, and I've suddenly diverted from that path, and something has gone wrong, is what I realized. And so I took some steps back and dealt with those and came out of that and got back on the path and became a follower again, because it's important to follow.
Okay, where can I see evidence that you were ever on this other path? Where can I see the evidence of that?
I think I might have left YouTube comments here and there on YouTube of like flat Earth videos from like 20.
Okay, no, did you make videos about it? Did you talk about it? Are there interviews of you speaking about flat Earth and alternative medicine or whatever? Can I go and see those?
I did, but the YouTube channel that I was featured on years ago got taken down. So
it got taken down. Oh, how convenient.
No, because they were posting some really controversial topics, and so it got taken down.
How long ago was this?
This was in 2019.
Oh, that's interesting, because so what? In 2019, you had a website, a YouTube channel that was showing all controversial stuff, yeah?
It wasn't my YouTube channel. I just featured on there.
You just featured on there?
Yes.
Okay.
But I'm sure I can find out some comments I made on Friday videos where I've shown.
Okay, so what name were you featured under? Because I'll search for it myself. Okay, what name were you featured under? You can't remember?
I can't remember because I used a
Wow.
different username.
Yeah, well, you know what? I've had lots of usernames and I can remember every one of them. So that's odd. You can't remember. I don't think, you know what? I don't think you're telling me the truth. Right? You're
No, I'm
making
being
out that you
genuine.
were
I
like
don't
me.
remember what the username was.
You're trying to say that you were like me, right? But I see no evidence of that because
No, what I
you know,
meant
if
by
you were
that,
like
look,
me,
I'm not
then
saying that
you would speak out about what you've learned, right? And
and I
I would be
did,
able
and
to
I
go and
did
see
my
your
part when I
footprint.
was. I did my
I
part
would
when
be
I
able to
was
see
in
your
that.
footprint.
I did my part when I was in
I
that
would be able to
state
see
of
your
mind.
footprint.
I don't even
Well,
know.
tell me your username. I'll go look on the Wayback Machine and see and find your stuff. So where can I find your stuff?
When I said I was like you, what I meant was like I went on this alternative path, and that's what I meant by that. I don't mean that I did everything you did.
So what you actually meant by that was you went on this alternative path as a follower, because you've
No.
already admitted that that's what you are,
No,
a
not-
follower.
Not as a follower.
No, you said it. You said you were a follower.
No, I wasn't. I said I was an advocate.
A follower. So you
No.
didn't lead, you didn't show anything that you found, you didn't do any of your own actual research and present
No, I
it,
did do
right?
my
You
own
just followed. You
research.
just,
I did do my own research.
where's the research?
I
Show
did
me
do
the
my own-
research.
all of
Where's the
that.
research?
I removed it.
Where's the research?
I removed it because when I look back at it, it just reminds me of a time.
Show me. Okay, you've got it. You must have it
I
saved
was
somewhere.
not in a
Show me your
clear
research.
state of- I was not in a clear state of mind, and that's why I went down this path. It was that simple.
Okay, I've got a book I started writing when I first started waking up, and I didn't publish
From
it because
what?
by the time I got to the end of it, I realized that the things I'd learned at the beginning were wrong. Okay, but you can actually go to my website and still find that book, right? Because it's still valid because I was learning at the time. So there's my research. Everything that I've learned, I've just put out there. Okay. Because I'm not a follower. You are a follower, right? So I'm not surprised that you flip flop, because followers just follow the one in front.
I never flip flopped. I came out of a state of mind.
Well, that's what you just said. You were like me apparently, and then you flip flopped because you went from the system. You flopped over to my way of thinking, and then you flip-flopped back to the other way. That's the definition of flip-flopping.
No. What happened was I was going through something and I came out of it. When I came out of this
Flip-flopping.
unnormal state of mind and went back to the normal state of mind, I realized, oh wow,
Normal.
that was something. That was an experience. And that's all that was. And I'm grateful to have come out of that because, you know, seeing you've obviously stored in this state of mind for, I'm not sure how long now it's been, a decade or something.
Where is this going to get posted? Because I can't wait to see this again.
I'm not sure because I think it's going to be a massive file with a lot of MBs.
Okay. Right, but is there any way you can actually like Dropbox it to me or something?
Sure, yeah.
Okay. All right, we'll leave it there because we're only going to be going backwards and forwards with this. So, and I've got stuff to get on with. It's 3.5 hours now. So,
yeah, no worries.
So, all right. Okay, so